The introductory course Geology of the Cayman Islands has been developed as part of Geology Education Week. Since 2013, this week is jointly organized by Dr. Brian Jones, Professor Emeritus at the Department of Earth and Atmospheric Sciences, University of Alberta, Canada, and the Water Authority of the Cayman Islands. Geology Education Week provides general and Cayman Islands-specific geology education to high school students and high school teachers in the Cayman Islands. Dr. Jones continues his geological research in the Cayman Islands, which he started 40 years ago, around the same time the Water Authority was established. He has shared his work and technical advice with government agencies and the private sector. Especially the Water Authority has benefited from his work. This video recording is provided as educational resource material for teachers and the wider public for non-commercial purposes as part of the Water Authority's 40th anniversary celebrations. If you use this video recording, please acknowledge Dr. Brian Jones and the Water Authority. This recording was made of the course given on the 24th of October, 2022. In November 2022, the book Geology of the Cayman Islands, Evolution of Complex Carbonate Successions on Isolated Oceanic Islands, written by Dr. Brian Jones, was published. This book provides a comprehensive account of the geological research conducted in the Cayman Islands by Dr. Brian Jones and his colleagues. For comments or questions regarding this video recording, please contact Water Authority, info@waterauthority.ky. This video has been produced by Cayman Spaces Multimedia Production. All rights reserved by the Water Authority of the Cayman Islands.
I'm going to apologize before I start. Usually I would stand to give these lectures. Unfortunately, I've got a really bad hip, and I can stand for maybe 5 minutes, and then I'll be a heap on the ground. So bear with me while I sit, and I apologize for this. As I go through this, I'm going to cover many different aspects of the geology. One of the problems we have in geology, even for somebody like myself, we have so much terminology. We typically have anywhere up to 6 or 8 different words for everything we deal with. It's a nightmare for us. I will do my best to keep the terminology down to a minimum. If I start using words that you do not understand, which is highly likely, please stop me and ask me to tell you what they mean, okay? I will do my best to define words as I go through, but I will slip back into geological talk very quickly. As I always tell all my students I've taught over the years, no such thing as a stupid question. If you don't know it, you'll be sitting there saying, I don't know that, but I don't want to ask the question. Probably everybody else in the room's got the same question. So, all your teachers, you know what it's like, the students don't behave like a student, ask the question. All right? So with that, we'll make a start. So I'm going to try and give you this morning an overview of the geology of the islands, which is going on. I'm going to do some shameless promotion here. There will be a book on the geology of the Cayman Islands. I was hoping it would be ready this week when I came here. I've had delays because of the publisher. It should be out anytime. I'm hoping anytime soon, but that's... Anyway, this is a book that covers, it's about 300 pages long. It covers all aspects of the geology of the islands. Obviously technical, but written in, I hope, in a way that people can understand. And I'm hoping that when it comes out, it will give you a good overview of the island. I've been coming here since 1981, so we've got 40 years of field work and analyses on which this is based. Obviously, this course today is sponsored by the Water Authority and myself from the university. I'm now retired from the university, but still active. So what we're going to do, first of all, we're going to talk about the tectonic setting of the islands. So we're going to start at a very large scale, because you need to know this. I'm going to define some basic geological terms. As you're going to see, it gets We're going to look at the geological succession of the islands. I'm going to look specifically at the geology and water production, so that next time you're drinking a glass of water that comes from the Water Authority, you'll know exactly what's gone behind getting you that water. You tend to think, well, it's just a glass of water. An incredible amount of work goes behind giving you that glass of water. The geology is the starting point. And then I'm going to take you on a tour of the island and show you some specific features. Some of these features we'll see on the field trip this afternoon. Other features you will know already and often perhaps wondered why they are there. So first of all, we're going to start looking at tectonic setting of the islands. And before I go any further, can the people at the back of the room, can you hear me okay? Okay. If I start mumbling, just throw something at me or get my attention. So, as you're well aware, unfortunately, this screen will not allow me to use my laser pointer. So I can use the laser pointer there. It disappears as soon as it hits the screen. So I'm going to, you'll have to try and follow me, and if need be, I'll wave my stick at it. For the islands, as you can see there, this is a view of the ocean, the Caribbean Sea. You can see Grand Cayman, Little Cayman, Cayman Brac. And the key feature that you'll see here is that sort of east-west line that goes across with a darker, deeper water to the south. So this is very important when we come to look at the structure. What this is all related to is what we call plate tectonics. And in particular, you have to visualize the Earth, the surface of the Earth, as not a contiguous, continuous mass of rock, but it's actually broken up and divided up into a series of what we call plates. And these plates have got various sizes, various structures, and when we look at these plates, we have to look at the boundaries of the plates. There are three types of boundaries. There are spreading centers. That's where the plate is generated. There are subduction zones. That's where we lose the plates. And there are transform faults in which the plates move laterally alongside each other. The important thing to note is, as is shown in this picture, no, I can't even do that way, can I? Okay. You're going to have to bear with me on this. As was shown there, any one plate can have all three types of plate boundary. So if we're looking at the African plate, for example, you look off to the west, you've got the mid-Atlantic ridge, which is a spreading center. That's where you're forming the plate. That is pushing the African plate to the east. And given that you've got other land masses around, you can't keep on forming new plate, and it's got, you know, what you generate, you've got to lose. So in part, this is then going to go down in the subduction zone. And then in other places, just to accommodate this, you will get these plates that move. If you were looking at a map view like that, you'd get the plates that would move this way beside each other. That's a lateral movement. That is a transform fault. Okay? So there we've got, or there's other terms such as divergent boundaries, convergent boundaries, and transform. So you can see in the bottom left there, that's where the magma is coming up from the center of the Earth, pushing the plates apart. The middle is the convergent, where the plates, one plate's going down beneath another, and the transform on the right-hand side where they're moving this way. So if you look at the mid-Atlantic Ocean, deep water, and obviously you've got Africa and South America, and I'll use that as an example. If you look in the middle of the ocean there, you see an area of shallow. So the lighter colors on this is the shallower water. So this is, in effect, this is a submarine mountain range. These are the longest mountain ranges on the Earth. You can trace it all the way from Iceland. You can come all the way through the North Atlantic, down to the South Atlantic, and then trace it around into the Indian Ocean. And the relief on these ridges is significant. It's as much as Everest in places. And you can see on the lower left corner here, this is a color topography showing you the structure of this ridge. The blue is the deepest, the orange is the shallowest water. And you can see there that if you look at that ridge that is going from the lower right to the upper left, you can see there is a dip in the ridge. And that dip in the ridge, think of that as a trench. So it's a trench. That's where the new magma comes up from the center of the Earth. So that magma comes up, pushes the plates apart. And that's going on all of these systems. Now, a subduction zone, this is where, so we've seen where the plates are coming up. At the other end of it, you can't keep on generating new crustal material, otherwise the world would be growing bigger and bigger, and we know it doesn't do that. So we generate new crust, we've also got to get rid of crust. And we do that at these what are called subduction zones. And this is where the crust, the oceanic crust there, is pushed down underneath the continental crust. So if you've got continental crust like that, you've got the oceanic crust coming here, it's pushed down. And the reason it goes down is that its density is a bit higher than that of the ground mass. And of course, as it goes down deeper, as we'll see, then you're pushing it down into high temperatures. It will then get melted to form a magma. Magma comes up, and that's why you get volcanoes often along these boundaries. So those are the divergent ones. Transform fault. See, the problem you've got here, we're dealing with a globe. So we've got curved surfaces. And while you can perhaps understand very easily, you generate magma that forces plates apart and then gets subducted, if this was just a flat surface, straightforward. But we're dealing with surfaces that curve in all directions. And that gets us into the realm of spherical geometry, which is a nightmare, but because you've then got to accommodate things. So the way that the Earth's surface accommodates it is through what are called transform faults. And a transform fault is where the spreading center, the mid-oceanic ridge, gets pulled apart. So here, and I am going to get up here and point because otherwise it's hard to follow. Just bear with me. So here, this would be the transform fault. Just, I can't touch the screen? Oh, you're kidding. So here's transform fault. It starts there, ends there. There is the mid-oceanic ridge, there it is there, they're offset. Transform fault is the only fault that has defined ends in this sense. And so if you look at the spreading, you can see if you're in this part, movement is in opposite directions. If you're in this part, they're in the same direction and the same direction here. And if you look at this picture, satellite picture of the South Atlantic there, you can kind of make out all of those lines that are going across the central part of the ocean. Those are all the transform faults. So there's hundreds of them that are doing this. The most famous of these, of course, is the San Andreas fault, because this is where You've got the East Pacific rise that actually goes under the North American continent, and the plates are moving in such a way that you've got the Pacific Ocean plate going to the North American continent's coming to the south, and therefore you get the San Andreas Fault. Why do you get earthquakes on them? The reason you get earthquakes on them is that when these things, so if you've got two plates moving like this, if they suddenly lock, because there's something underground that is locking them, that doesn't mean they've stopped, it just means they're locked. And then with time and pressure, that will be released and they'll just do that. And that's what gives you these massive earthquakes. So in some places, this is done gradually, you don't feel it, but places like the San Andreas Fault is where you get these massive earthquakes because of that lock-in on it. And you can see on the photograph on the right, this is in the some of the desert areas, you can very clearly see that fault line with the strata on either side moving across, moving laterally. And then if we put all of this together, we can define the major plates. So for example, we're showing here the Pacific plates, and we've got the Atlantic plates, etc. You notice that the red dots which show the volcanoes, most of the world's volcanoes, not all, but most of them are all tracked around the coastal areas where you've got these plates subducting below the continental plates. And you get the other ones. You'll notice that there are some dots in the middle of the ocean, such as the Hawaiian Islands there. These are a different structure than what we call a hotspot. I'm not going to go into that because we haven't got time for doing that. So how does this apply to the Cayman Islands? Well, if you think about it, we're dealing with a sphere. But we're now into the realm of spherical geometry. It's impossible to get plates that all fit nicely together on that surface. There's 7 major plates, but they don't all fit together very nicely. And in some areas you get small areas, they're almost like a jigsaw puzzle where you fit pieces in to make the rest work. And that's exactly what happens in the Caribbean. You're at the junction, you've got the North American plate where USA is, you've got plates coming in from the Pacific, you've got the Atlantic plate off to the east, you've got the South American plate to the south. So they're all fighting for space, is the best way of viewing it. And this is one of the areas where it becomes a very complex jigsaw puzzle. So basically, in the simplest sense, millions of years ago, the isthmus between North America and South America didn't exist. We had a plate that came up, hit the North American plate, then went to the east, filled in the isthmus between South America and North America, and as a result, here in Cayman, you're sitting on the edge of a plate, and you've got these transformed faults. So if we look at these pointers if we look here, you see that distinct line going through here, south coast of Cuba, Cayman Brac, Little Cayman, Grand Cayman there. You're sitting on the edge. There is actually a small spreading center off the southeast corner of Grand Cayman. So you've got a very short spreading center. So we're pushing land here, the ocean floor is going that way, here the ocean floor is going this way. So that's the setting that you're in here on Cayman. That's why you get earthquakes here. And the good thing here, from your perspective, is that these earthquakes happen all the time. So although you don't know it, you probably get about 2 earthquakes a week here. But most of them are so small that you don't get them. I remember many years ago, Department of Environment, Fred Burton got in a seismograph and installed it, and was shocked when he found that he was recording 2 earthquakes a week on average. But they're so small, you don't feel them. But every so often you get a big one. And that, you know, the good news here is you're getting small ones, because that releases the tension. So when you get a big one, it's not as bad. So that's where it's you're looking at here in terms of the settings of the islands. So here it summarizes it. You've got the mid-Cayman rise there shown in red, shows you the islands. And in the lower part, there's a cross-section that goes from the western part of the Caribbean across into the Sierra Maestra of Cuba. Another critical point on this is that this ridge, and it is a ridge, it's a submarine mountain chain in effect, is also, so we've got this ridge going east to west, but then there are also faults going north to south that segment that ridge into different segments. So Cayman Brac is on a different block than from Little Cayman is on a different block from Grand Cayman. And this is also important because if you look at the history of earthquakes, for example, Grand Cayman's got a long history of these earthquakes. Cayman Brac, Little Cayman, very few. And it's all related to it. This is why Cayman Brac the island has been tilted like that. So you've got high land at the eastern end, and you go to Little Cayman, it's only just above sea level. They're on different units of rock. They behave differently. And they behave differently from Grand Cayman. And this has an enormous importance for, not just for people living here, and you may wonder why I go through this, but this has enormous importance for understanding the geology of each island. And that also then feeds back into understanding the hydrogeology and where you get the water from. Everything is connected. So we have to understand this. I'm not just presenting this for the sake of presenting it. I'm trying to give you the background in which we have to view the geology and everything that goes on with it. So, say there's a picture of one of these satellite pictures. You can see the Orient Transform Fault off the south coast of the islands. You've got the Cayman Trench, you've got the spreading center, incredibly deep water in the trench, as you well know. And there's the motion of the North American plate against the Caribbean plate there. So that's what's generating the earthquakes that you see. If you look at the wider picture here on this, all those red dots are all what we call the epicenters. These are the points from which the earthquakes are generated. And you can see that Cayman gets a lot, but nothing near as much as you get on Jamaica and the other islands. So that's the good news. You get earthquakes here very frequently, and most of them you don't even feel. You've got to get up in that 4 to 5 range and above on the Richter scale before you will start feeling. The good news here is that the earthquakes are so frequent. Because of their frequency, then they're releasing the pressure and tension. It's not being allowed to build up. Every so often it gets stuck and then it goes. So, before and I apologize, I should have told you at the beginning. As I talk, don't be shy. If you don't understand something that I'm saying, stick your hand up, ask the question. No such thing as a stupid question. right?
Is it the frequency of the earthquakes that allow them to be not so?
Yes.
It's
Yeah.
not the type of fault. Or
No. It's the frequency of it. Imagine, I don't know, well, none of you live like I do in the freezing cold of Alberta in winter, but it's like if you're stuck on ice, you know, if you can get going a little bit, you're okay, but if you're stuck and then you put the foot in the gas and then you take off. So the more frequent the earthquakes, the better, because you're releasing it. So imagine, you know, you've got these two plates like that. And the way I do it, if you put your thumbs and you lock them, then it's still moving. You're just pushing and pushing and pushing. And then all of a sudden it'll go and you'll go. So that's what the secret is. Yes?
Yes, going back to subduction zones.
Yep.
Where the less, when you have two converging plates where the less dense one goes beneath.
Yes.
You have a case where you have, say, two oceanic or two continental plates
Yep.
with the same density.
Well, what happens then, and the best example of this is if you look at the Himalayas. So long time ago, when India started moving across the Indian Ocean, and then it went in and met the Eastern European plates, they're both crustal material, so there's no density difference. So what they do is, as they came together, they squoze out the ocean deposits that were between them. That was lighter material, pushed it up. And that's why you get the mountain ranges there, okay? So it's, imagine that you've got a vice and you gradually close the vice jaws together and you're squeezing the material up in between. That's what forms the mountains in the case of the Himalayas. And I stress that because not all mountain chains form by that process. So if you looked at the Andes in South America, that's a different process. Okay? So does that answer your question? Yeah, okay. All right, yes?
What explains now the frequency of tsunamis? The frequency of tsunami.
Right. So tsunami is created when you've got, typically it's created when you've got an underwater slump of material. So if you imagine you've got a coastal area, you've got sediments forming beside the coast. If that fails and you get a block of that sediment goes down like that, then as it goes down, it pushes the water back up. So you've seen examples of this historically. In my memories, 1700s, there's the big tsunami in Port Royal in Jamaica, and that's caused by a slump of the offshore sediments. Literally what happens is the offshore area fails, the block goes down, and as the block goes down, it pushes the water up. Okay? Any other questions on these? Right, so let's turn our attention to geology of the Cayman Islands. You perhaps understand why I've given you this first introductory part. You need to kind of understand that to understand the geology of the islands. And on the face of it, you would think you've got three relatively small islands. Geology should be simple. So put this in perspective, I've been working on these islands the last 40 years. I do other projects as well, but I've had innumerable PhD students complete their thesis on the island. Numerous MScs were finished. We understand a lot about the geology islands, but there's also a lot of it we just still do not understand. Okay? So I'll do my best to explain it. So typical rocks on this island look like this. This is in the Jennifer Bay Quarry on Cayman Brac. They're white, they look massive, they look featureless. And you go, what's so difficult? Well, we're going to see. Because when you start looking at the rocks and details, you get outcrops like this, and you look at it and you stand there. When my graduate students and I first found this particular outcrop on Cayman Brac, we stood there, looked at it, scratched our heads, and then had about a couple of hour arguments about how we could possibly form it, because it's a mess. This is just a mess. The problem we had here is trying to determine what was the original rock and what replaced it and how it replaced it. So just to give you an idea of what we're dealing with on some of this. Again, shameless promotion here, there is a book. If any of you are interested in the origin of carbonate sedimentary rocks, there is this book that I co-authored with one of my colleagues some years ago. This is the one we use for text in the universities. So modern carbonate sediments. You are blessed in this area that you can simply go out, jump in the ocean, and you can see how carbonate sediments are forming. So when you jump in the ocean, you see all these wonderful corals of different species and genera. All of those skeletons are formed of calcium carbonate, which is the building block of the sediments. You can see the sediments are forming around. As I'll show you this afternoon when we're in the field, all of these sediments are formed of small grains that most of them have come from the corals, the breakdown of the corals and the other organisms that are there. So this is the carbonate environment. And one of the things that I've always found great about working on these modern sediments, I have an excuse to go scuba diving and snorkeling. I should also point out, I spent 10 years working in the Canadian Arctic, so it's a very different environment. But this is one of the attractions of it. So this is what these rocks start. You've all seen the rocks around Cayman, you know what, but this is what they start life as, in these wonderful environments. And then they get transformed into these hard, massive rocks. And these are formed of CaCO3. They're formed of the minerals calcite, aragonite, and then on a lot of this island we'll get dolomite. And I'm going to explain these terms to you very shortly. So characteristic rocks around here are these white, hard rocks. Again, looking at the different, just to give you some feel for these environments, I'm sure you've all been swimming, snorkeling, diving around them, so you've seen all these. The sea fans, the upper right there, these dense colonies of corals. Lower left here, these mounds of sediment. How many of you have ever seen these mounds of sediment and gone and looked at them in detail? No one. If you look at them in detail, right at the top there's a little hole. And these are formed by burrowing shrimp. And they actually have a very complex network. If you dig down, you'd find tunnels going off in all directions on the ground. And again, in the lower left or lower right there, we can see the same thing. Now I gotta get technical. On the face of it, all of this sediment is formed of calcium carbonate, CaCO3. Probably one of the simplest minerals compositions that you can see, compared to some of the other minerals we deal with. But it's not simple. And I will tell you up front, there's a lot about this crystal system we still do not understand. So simplicity doesn't mean, simplicity in the chemical formula doesn't mean that it's simple to understand. So with these, we have what we call three polymorphs. I got back up a little bit. By definition, a crystal or a mineral must have a specific composition or a range of composition specific crystal structure. Those are the two main issues. We can have the same composition but two different types of crystal structure. And that's therefore becomes two minerals. When we get this situation, these are what we call the polymorphs. So now we've got to look at the issue of the polymorph of calcium carbonate. There are three of them. We have calcite, which is CaCO2. Don't get bogged down in this terminology. Trigonal system, which is a three-fold axis of rotation. We have 6 different crystal systems, and calcite belongs to one of them. Aragonite is another, same composition, calcium carbonate, but different atomic structure, different crystal form. We have a third one, vaterite, again, calcium carbonate, hexagonal system, and along the bottom there you can see various pictures of these. Thankfully, vaterite is very rare, so we don't have to worry about it. All right? Calcite and aragonite causes me enough headaches without having vaterite to worry about. So if you look at those sediments that you see in the ocean, they are mixtures of calcite and aragonite, all mixed together. Color plays no part in defining the mineral. No part whatsoever. So the picture that I've shown you at the bottom there, those are 4 pictures of calcite. So one is clear, reddish, black, brown. Color has no part in defining a mineral, because the color is a reflection of minute amount or trace amounts of elements. Yes?
One is saying, thankfully, vaterite is not common. What are you implying by that?
I've never seen vaterite. That's how rare it is. It's because it's a very unstable form of the calcium carbonate. So you've got to have very specialized settings for it. It's found in some caves in various places, but not every cave. So I've never seen, I mean, I've seen vaterite, I've picked it up. I've never found vaterite in its natural form. Okay, and you would talk to most people that specialize in carbonate sediments like I have, and they will tell you exactly the same thing. And I've worked in carbonates all over the world in all different settings, never seen it.
Do you think it's because it doesn't?
You've got to have really specialized conditions to it. And I'm going to give you a very vague answer. I cannot answer that because we don't fully understand it because it's so rare.
Okay, is it because maybe it doesn't survive?
We don't know if it's because it's not being precipitated or that it's not being preserved, right? So for example, if we form aragonite in the natural setting, which is common as I will show you, with time aragonite can change to calcite. Can't change calcite to aragonite, but you can change aragonite to calcite. So, but that takes time. If vaterite is forming in some of these, it could be that it's not stable enough and it changes to one of the others very quickly. If you go into the geological literature, there are so few papers on this that all we can say is we don't really understand it. Okay? Now, just to show you why we get into trouble on this. This is a very, if you look at that, it's a very simple diagram. We've got pressure on the left, on the y-axis, going from 0 pressure to high pressure. We've got temperatures on the horizontal axis going from 0 to 400. This is a simplified diagram of a graph that is produced by laboratory experiments. And what you can see, according to that graph, at low pressures, low temperature, we should get calcite. Remember, So when we're dealing with the oceans around here, we're down in this corner, right? Because we got low temperature, maximum temperature would be about 35 degrees Celsius, is essentially close to surface pressures. So according to that, everything that is precipitated should be calcite. We shouldn't be getting aragonite at all. But unfortunately, nature has other ideas. So the corals that you pick up around Cayman, shown on the right, the Millipora on the right there, their skeletons are formed entirely of aragonite. Look at the Strombus gigas, the conch shell on the left. That shell's formed of aragonite. I can show you a whole list of organisms that live in these oceans around here, and their skeletons are all formed of aragonite. According to the geochemists, according to the labs, this shouldn't happen. But you remember now, it's the animals, and we've got some of the plants, some of the algae, and some of those also precipitate aragonite. They do what they want. They don't worry about what we tell them or what is known from the labs. So within their systems, because they're now dealing with biological processes, within their systems, they are capable of producing aragonite. They prefer aragonite. Complicate it even further, not all animals want aragonite, some like calcite. And somebody's going to ask me, well, why? And I'll be very honest, we don't know. We simply don't know. Because people have tried this, they've tried everything to resolve this problem. We have not yet succeeded. So it's one of the reasons that I enjoy working with carbonate sediments is because of the animals and plants, be they modern or in the ancient rocks which I've dealt with. On the other flip side, they drive me crazy. That's why I've got no hair left. It's because we don't understand them. Everybody's tried their best to do it, and it gets worse than that, but I'm just giving you the simple version of it. So what we've now set up, though, and think about it, all these corals are formed of a mineral that is not stable. It's stable in the skeleton of the coral. As soon as that coral dies and life functions stop, if we start then putting fresh water on it, for example, the aragonite will either dissolve or it will transform to calcite. Just to cause us trouble. I shouldn't say that because that's what's given me my career in part, so I have to be grateful for this. But this is the situation, but this also is very important for things like water resources and that, as I will show you. Now, I'm going to stop here. I'm going to allow you to, please, if you feel it, go to the washroom, refresh your coffee, stretch your legs. But before we do that, has anybody got any questions on what I've covered so far? I realize, I've bombarded you with a whole lot of new terminology and ideas, and I've tried to keep it as simple as I can, but I realize in part I'm probably even speaking a different language. Yes?
So when the corals die and that aragonite is there, does it degrade? It's like a degrading, does it degrade, or is it just a simple conversion? Is there any?
There's no, forget the word simple.
Okay.
So what happens is, if you take a coral, it dies.
Yeah.
While it's on the sea floor, probably nothing's much going to happen to it. But you start burying it with sediment, and then that keep on doing that. So now it gets down to depth. You put it into a different environment. And it might well be that by the time it goes down there, you're getting fresh water flushing through the system. Now, as that fresh water goes through, one of two things will happen. Either it will dissolve the skeleton, or it will change it, the aragonite, to calcite. Why it does one in one situation and a different thing in a different, we don't really know. We think it's due to, it could be due to temperature controls, it could be due to variations in the composition of the waters, the depth, how deep you are. People have tried to solve this for years, and every time you think you've got the answer, then you find another setting where it's quite different. So there are even very rare examples where the aragonite is preserved. So some of the oldest aragonite we know of is still preserved in shells of Devonian age, which are, 300 million years old plus. So I can't give you a straightforward, definitive answer. You're going to hear me say that quite often. As much as we know about geology, there's a lot we don't. And this is one of the problems that we have. We like to see the aragonite preserved because then we can do a lot of different types of analysis, give us a lot more information. But generally that's some of the rarity. So a lot of the bedrock that you see on Cayman, for example, the bluff, the old hard rocks, the aragonite's all gone. There's none left. You look at the Iron Shore Formation, we can pick up some of the corals there. They're 125,000 years to 300,000 years. Some corals in there are beautiful, still got their original aragonite. Others have been changed to calcite, and there's no pattern. I mean, I've seen the situation on Cayman. We've gone to the Iron Shore, collect two corals almost side by side. One's still aragonite, and the other one's partly changed to calcite. So the problem we have is that all of that sort of thing operates on a micro scale. And we're having enough trouble as geologists dealing with a larger scale. So when we get down to this sort of micro scale, we're commonly in trouble. And people have tried to model this in laboratories. It's very difficult. I mean, it sounds as though it should be easy, it's not. So we still have trouble understanding. Please. Any more? Yes?
The Cayman Trench and the Puerto Rico Trench, they're both on the Caribbean plate?
Yeah.
Are they formed at the same time, or?
They're the same. They're just, you're now superimposing geographic terms onto geological structures.
Both the Caribbean plates.
And you'll see, actually in some cases, you'll see the same trench with different names, depending on who's writing the paper. So Cayman claims, Cayman Trench, and Puerto Rico want their name, and that's when geography and geology come together, you get this issue.
Why isn't there above Hispaniola? Why isn't the trench doesn't run through there?
No, the trench goes straight across.
Oh,
Yeah. So it runs south of Cuba. Mm-hmm. So what I've done so far is to sort of give you a overview of the structures of the world and where Cayman sits, and basically giving that idea. What I'm going to start doing now is focusing specifically on the Cayman Islands. And you'll see it. So one of the things you have to deal with here is geological time, which is not something that most people worry about. Of course, we have a classification. We have classifications for everything. And as you'll see, the Phanerozoic is the eon. We're in the Cenozoic era. We're in the Tertiary and Quaternary periods. Tertiary we can divide into Paleogene, Neogene. Don't worry about those two terms. But what is critical from the point of view of Cayman is that the rocks that you find on the Cayman Islands are embraced by that red line that I've shown you. So if you want to see the oldest rocks anywhere on the Cayman Islands, go out to the east end of Cayman Brac, and where the rocks in the cliff faces there, lower part of the cliff faces there, you're into the, best we can tell, the upper part of the Oligocene. So you're looking probably around 30 million years. Now, remember when we deal with geology, they put numbers like 5.2 and all this on there. We're not that accurate. There's quite a wide margin of error on some of these things because of the problems we have. So most of the rocks here are what we would put in the Miocene, Pliocene. So when you look at the bluff around the hard rocks in the core of the island, those are Miocene, Pliocene here on Grand Cayman. On Grand Cayman, we do not see the Oligocene unless we drill down very deep. And then the Iron Shore Formation, which you're also familiar with, that is Pleistocene. Okay? So we're going to see examples of rocks from the Oligocene, Miocene, Pliocene, and Pleistocene. And the Holocene, that's basically modern sediment. So when you pick up sand on the beach, that's what we would call Holocene. The next term I've got to introduce you to is the term formation. So you can imagine that when we're faced with the cliff face on the east end of Cayman Brac or any other succession of rock we've got, we have to have a way of classifying it and a way of communicating about it. So we break, if you can imagine the sequence of rocks, we will split these into what we call formations. And each formation will have its characteristic set of features, which will be different from the formation above it and different from the formation underneath it. So in the simplest sense, we could say this formation is formed of limestone, the one above it's formed of dolostone, or dolomite. It's a way of classification. So, as it says here, technically, a formation refers to a package of rocks that are all similar to each other, but different from the rocks in the packages above and below. So that sounds simple. It's not always that simple to deal with. I'll show it, and here we've got an example. This is taken in Pedro Castle Quarry many years ago. We will see Pedro Castle Quarry this afternoon. Unfortunately, it's so overgrown now, it's very difficult to see it in detail, but it used to be clean. And you see where one of my graduate students has perched part way up. Right at his head, top of his head, you can see a change in color. Now, color for us does not enter into the argument, because color is a function of weathering. And once, for example, the lower rocks, they're whitish, give them another couple of 1,000 million years, they're going to be gray. They can change. Color does not play a part. It's convenient here because that forms a nice boundary. It appears to be very flat and straight. It's not, as we will see later on. But it does highlight, so underneath we have what is called a Cayman Formation. It's formed mainly dolostone, formed mainly of dolomite. Dolomite is a calcium magnesium carbonate. Pedro Castle Formation is formed of dolomite and limestone. So the limestone is just calcium carbonate. Dolomite, calcium magnesium carbonate. Okay. Very difficult to tell just by looking at a rock. But the easy way of distinguishing these, as we'll see this afternoon, I hope, if you use 10% hydrochloric acid and you just put a drop of that on the rock, if it's limestone, it will react. If it's dolomite, it will not react. It's a simple, very safe way of doing it. 10% HCl, I wouldn't advise it. You could drink it, but it wouldn't, I mean, please don't go and do that. But it's a very weak acid that will not have any effect. So there's an example here. The other formation we deal with on this island is the ironshore formation, such as the outcrop shown there. The other thing we have to worry about is between these packages, there are boundaries. So in that quarry, the wall of the quarry, I showed you the boundary between the Cayman Formation, Pedro Castle. These are typically, not always, but on this island, the boundaries between the formations, the weathering surface. These are periods when the islands were exposed. So think of Cayman Brac that's shown here. You see the land surface, you can see the cliffs at the east end. So this is a view looking to the west, and then that surface slopes down to the west. What I want you to imagine now, you've got to start visualizing one of two things. If the sea level stayed where it was and the island sank down, which it could do, then as it sinks down, the ocean starts covering the island, you start depositing sediments on top of it. The other option is that sea level can go up. And as the sea level goes up, it will also cover the island with sediments. And you're going to bury this weathered surface. Now, if we bury that weathered surface, that is what we call an unconformity. So if we get a bed of sediment laid down like that and another one on top of it, another one, we say that is conformable because they're all parallel to each other. If we get a break in sedimentation, that's what we call an unconformity, which may commonly is a weathering surface. And you'll see the importance of this in a minute. I want you to visualize. Imagine that that island stayed where it was. Sea level goes up, it will be flooded at the west end first. We're going to get sediments deposited there. Goes up enough, it'll bury the whole island. And then all we would see in that would be a boundary between the two. So that's what we're looking at. And at the bottom there is a three-dimensional model. This is looking from the sort of south at the island, what we've just seen. So the high rocks at the east end, low rocks at the west end. So that's what you're going to flood and deposit sediments on. Unfortunately, when we see this in the rock face, and this is a view in the quarry at the west end of Cayman Brac, you'll notice about halfway up that photograph, there's a change in color from a gray to a white. There are other features with it. Most of the time you just walk past that. Certainly if you weren't looking for it, just, oh, it's a color change. That boundary is actually the boundary, we think, between the Oligocene and Miocene. So that surface could represent an enormous length of time. It can actually represent more time than the rocks that are preserved. And that's where this is where life gets interesting. Because trying to recognize it took us a long time to recognize these. Because this is on a clean surface. Imagine this is weathered and covered with stuff. It then becomes difficult to recognize. So now, bearing those concepts in mind, I've shown you what a formation is. I've shown you what an unconformity is. There are many different types of unconformities. I won't go into them all. You need to just worry about ones here on Cayman. So I'm going to take you to the east end of Cayman Brac, where you've got some really nice exposures in the cliff face. So that's, sorry, let me just back up. So how do we get all this data together and work with it? One is we do very detailed field work. So you'll see us scurrying up cliff faces, not that one, but anything that's accessible. I do not ever go on these where I've got to use ropes. I've got enough to deal with. I've got hammers and collection bags and note taking. You can only do so much. So if I can get up there, I'll go, but not if I need ropes. Other types of data, so on the left there, it's showing exposures of the island. I've worked here for the last 40 years on the island. The first time I came down here was 1981. And I've come down here just about every year since then, apart from the COVID situation. Yeah. So during that period, we've visited just about every outcrop on all the islands, including ones that no longer exist. So if you think about the peninsula here and the western end of here, we came 40 years ago, there was hardly anything built here. Now everything's covered. So that means nobody can check my work. But so there is a benefit to it. So the other way we do this, we have to rely on drilling. When we're drilling, we keep very detailed notes on speed of drilling, etc., etc. We can either collect pieces of core, which is shown on the right-hand side. That's a slow, very expensive way of doing the work. Or we will collect well cuttings, like, so when he's drilling, imagine when you're drilling into a piece of wood, you get all the wood shavings coming out. Same in the rock, we collect those. There are limitations, but sometimes the economics are such that we have to do it this way. And I've got this slide. So the task we have is, if you find a rock face like this, we've got to try and make sense of it. And this is where life gets interesting. So, because you've got to take those sediments, transform them into a rock, and that's not the end of the story, because if you then change climate conditions and so on, you can then change the rock again. So these things, they appear static, but they're always evolving. So that's what we've got to deal with. And so we've got core, we've got well cuttings. This is the geological sequence that it's my group that have defined this sequence on the islands through the work we've done. At the base there, we've got what we call the Brac Formation. The only place you see the Brac Formation is on the east end of Cayman Brac in the lower part of the cliff face. It's the only place we found it. We have found it in wells, drilling and that. Cayman Formation, which is formed, we used to at one time think it was formed entirely of dolomite, entirely of dollostones. Some years ago, we actually found in a couple of the wells here in the east end of Grand Cayman, it's actually formed of limestone, just to cause more chaos. You'll see in this formation lots of corals, bivalves, forams, red algae, calcareous algae, gastropods, all sorts of evidence of life. It's as if, same what I showed you before in modern lagoons with all those life forms. That's what would have been here. Pedro-Castle Formation that overlies it, again formed largely of dolostone, but it's got some limestone in. Similar biota in it. Separating the Pedro-Castle Formation from the Cayman Formation can be very difficult. If I just go to an outcrop and there's one patch of rock, or you give me one piece of rock, I may or may not be able to tell you which formation it's from, because the rocks are very similar. And then we've got the iron shore overlying it. You're all familiar with the iron shore around the island. That's formed entirely of limestones with corals, bivalves, gastropods, and everything else. And then most modern deposits, of course, are the swamp deposits associated with mangroves and that. So that's what we're dealing with. And I'm going to take you through this now and show you these different sequences. What I want you to understand here, there's two other terms that we need to look at It's called transgression versus regression. So in the simplest sense, if this tabletop is my land surface, if the sea level rises over the top of that table, that would be a transgression. If the water is above the table and then goes down, that's a regression. But note here, this is a relative thing. So we can achieve that two ways. I can have the tabletop stationary and I change sea level, or I keep sea level stationary and change the position of the tabletop. It produces exactly the same thing. So summarized in this diagram here, if you've got transgression, so we start in the upper left corner with the ocean around the land, sea level the land sinks, I've got transgression because I've now got the ocean covering the landmass. And below, I've got the same thing as I started with at the top, land and the ocean. Ocean level goes up, it floods the land and gets sediment. Yeah.
By what process would the land sink?
Oh, very easily.
Just
Yep, that's just all it is to do related to the tectonics of the area, fault positions. You can that's not a problem. And remember here that I told you before that you've got the Cayman Ridge, you've got Cayman Brac, Little Cayman, Grand Cayman. That ridge is not continuous. There are faults. So you've got fault off the south, but you've also got faults between the islands. And we've got evidence, as I will show you, that Cayman Brac has behaved very differently from Little Cayman. And
fault movement.
it's fault movement, yeah. And you know yourself, you can stand on the west end of Cayman Brac, you can see Little Cayman, but there's a fault between them.
Yeah.
So faults can do this. Sea level can rise and fall according to the generation of the ice caps. So if we start melting the Antarctica ice cap, sea level is going to go up.
Is that similar to isostatic?
Yeah, this is isostatic.
Yeah.
Yeah, it's isostasy. I didn't want to use, I'm trying to keep terminology out. It is isostatic. Yeah. Yes?
So when you just say speed, does that account for what happened to the bluff, Cayman Brac? Because realize most of the island is a notch.
Right.
Notch right
On Cayman Brac, it is complicated, but we've finally, after many years of work, think we understand it. So what happened on Cayman Brac, I've presented this in a simple up-down process. On Cayman Brac, it's complicated because not only did it go up, but it tilted like that at the same time. So that made, as you perhaps following me, there's always more complications. We're dealing with nature, and we don't understand nature. But so for Cayman Brac, the land, when it went up, or it didn't just come up and down, but it came up and tilted. And that, as best we know, that probably happened in the Pliocene. Okay? The movements of land like this, of isolated islands, is very, very difficult to date precisely when it's happened. Okay? So basically what you're looking at on the Cayman Islands had the Brac Formation when sea level was high. We had a period of no deposition at the end of the Oligocene when sea level was low. Cayman Formation when sea level came back up again. Then a break when the sea level went down, and Pedro Castellano Show. One of the huge problems we have is, if you ask me, okay, well, how much did sea level go up? Very, very difficult. This is one of these almost impossible questions to answer. We got rough ideas based on the fossils that we find in it, but it's invisible. So we try. Anyway, that's what we're looking at. So let's have a look at some of these. We'll start with the Brac Formation and show you what that looks like. So we're down where the red arrows are. We only see the Brac Formation exposed on Cayman Brac, and you only see it at the very east end in the lower part of the cliffs. Despite the fact that we've had wells drilled at various points on the Brac, each of those red dots are where we've had wells drilled. We lose it. Unfortunately, the drilling equipment on the Brac can only go to a depth of about 200 feet. So we're limited in that respect. So we only see the Brac Formation at the very east end of the island. We don't know where it is on Little Cayman because there's been no wells drilled there. We detected it at depth on this end of Grand Cayman, but here it's at a depth of about anywhere from 250 to 300 feet below the surface. So again, it illustrates to you the differential movements. So at the east end there, you can see it. We don't see it anywhere else. So that just makes our life a bit more complicated. So what I'm going to show you, some of the pictures of the Brac Formation are all from that east end of the Brac. If we go there, this is on the north coast, which you can get to. It's not the easiest place to go. You've got to be prepared for some rough walking, and don't even try it if the sea is rough. You'll get washed away. So you've got to wait for a calm day, good walking, hiking boots on, and then you can scramble there. So here, and this kind of highlights the problem that you've got. If you look at that cliff face like that, it all looks the same. But there's one break in there, that one line where I've got the yellow line, that is the boundary between the Brac Formation and the Cayman Formation. That line represents millions of years of weathering. When you look at rock succession, we only see part of the picture. And often these lines represent more time than when the rocks were deposited. So we see the Brac Formation in the lower part and the Cayman Formation in the upper part. The first record of any geological work done on this is a paper published in 1926 by Charles Matley. Charles Matley was the official geologist based in Jamaica. And he came over and spent, I think it was 3 days on Cayman Brac, 2 days on Little Cayman, and 5 days on Grand Cayman. And it was a remarkable job he did, because his map for Grand Cayman, for example, is not much different from what we produce now. He's a really remarkable individual. And he was the first one that made any comments about the Brac Formation. There, the Brac Formation is formed of limestone. Cayman Formation is formed of dolstone. We have that very sharp boundary between the two formations. If you look at the limestone, it's dense, hard. You need a small sledgehammer to break it. And if you look very carefully, you don't find many corals in it. You get the odd coral. We get some bivalve shells. But we get, if you see here, there's that structure there. That is a cross-section of what we call a foraminifera. These are sort of disc-shaped organisms that live on the seafloor, and some of them will float in the oceans. These are very large. Some of these get up to about 5 centimeters in diameter. Most foraminifera are very, very small. You can barely see them. These are exceptional. And these do allow us to get a date on these rocks of that Oligocene date that we use on it. And if you look at the cross sections, these are the thin section photographs We make a lot of use of thin sections of these rocks to analyze them in detail. I won't go into detail, I'm just showing you how we get this information. Now, I said to you that the Brac Formation is formed mostly of limestone. You do get, on the north coast it's limestone, but on the south coast it's dolostone. So just that short distance between the north and south coast. What we do in thin section, if you'll see at the top there, you'll see those reddish colors. What we do in the thin sections, we stain them. There is a stain that we can use that allows us to separate calcite from dolomite. So anything that's red up top is calcite, would be the limestone. The white would be the dolomite. And if you look at the bottom ones, you can see very nice dolomite in the lower left there. And then if you look on the right-hand side, right here, you can see there's a dolomite crystal, but we're still seeing a ghost structure of a foram. We see a ghost structure of an algae that have been replaced by the dolomite. So it's a very nice formation to work on. I wish there was more of it. So it's got all sorts of interesting geology stuff on it. In terms of age, I don't want to go into great detail. Trying to date these rocks is a nightmare. We can use the fossils, which is what we do in most other areas of the world. Unfortunately, here in the Caribbean, there's been insufficient work done across the Caribbean that we can do this. So we can get a rough idea from the fossils. Then we have to revert to other geochemical things. We use strontium-87, strontium-86 ratios, which we get from these rocks. And that allows us to give a date on these rocks because that ratio changes with time. So I'm not going to go into details, but just to let you know how we deal with it. And that, if we use that strontium-87, 86, it does give us that upper Oligocene age to the rocks. This is this is on the south coast, which is a much safer area to go to. You can see this very nice. And what is really nice here on that is if you look at the cliff face, you've got the Brac Formation at the bottom, Cayman Formation up top. Where I've got those yellow lines, that is the unconformity that separates the two formations. You'll notice that many of the caves that are in that lower unit, the roof of the cave is flat at the unconformity. And if you ever go into the big cave system, if you ever go out to the east end of Cayman Brac, there's a ladder you can get up to one of these caves. And if you go in that cave and look at it, it's got a flat ceiling. It's as flat as the ceiling here. Unusual for caves. But that's because that flat surface is the unconformity. It's really nice. And a view of it. If you ever go out there, don't go too far along the coastline. If you get exceptional days, when the sea is flat, you can actually get quite a long distance around there. Don't try it when there's waves. You will not be seeing it again. So I think I've been able to get along there about 3 or 4 times in all my visits to the island. It's a beautiful area to go to. This is what the rocks look like. This is what we're dealing with. Now, I show you that and it's like, oh, so what? But now we've got to start worrying about the issue of porosity. Porosity is the amount of void space in a rock. It's the percentage of void space. So here, in fact, all of these holes in here, remember I was telling you about the way that aragonite and calcite behaves? So all of these holes here are actually foraminifera, or used to be foraminifera, that had aragonite skeletons. The matrix material between them was originally calcite. So when fluids have flown through, they've dissolved the aragonite of the animals. And sometime later, we've also changed the matrix to dolomite. But so a lot of the porosity in there, well, that's all because of the animals who originally had aragonite skeletons, which have now dissolved. Remember what I showed you first thing? You're not supposed to get aragonite forming. The animals don't care about our lab results. So that is actually a rock with very high porosity. And the other, this is also what you'll see in the Brac Formation. This structure in here and there, those are where you've, if you get, everybody know what I mean by a bivalve shell? If you get an oyster or something like that, that's a bivalve. So you've got two shells like that, a cavity in the middle. And in this case, the shells again are aragonite. They've been dissolved, they've gone, the void is left, and you've got nice big cavities in there. The reason I'm starting to emphasize and point out the issue of these cavities, these become important when we're looking for water for drinking. Okay, that's the connection. And I know this photograph doesn't look like very much, but just at the top of the handle of my hammer on the right, you can see a line going across the picture. That line is the boundary between the Brac Formation and the Cayman Formation. The deposit that you, not having a pointer here, this deposit here, that's a deposit from a spring. And at one time, there used to be a spring that came out of there, the waters come down and precipitated the calcite on top. We've seen evidence of these springs at 2 or 3 locations on Cayman Brac, associated, usually typically associated with boundaries between the formations. But this is not active now, as best we can tell. I've never seen it active. But at one time, there was a spring there. Just an interesting sort of sideline. So you've seen the Brac Formation. I'm going to take you in the Cayman Formation. Cayman Formation, very widespread. We see it over most of Cayman Brac. We see it all over the island here on Grand Cayman. Little Cayman, we're having trouble there because the outcrops are so scattered and so poor. You know, you just see a little bit of an outcrop. Very difficult to deal with there. We're still trying to get a well drilled over there so we can get this sorted out. So for Little Cayman, possibly we've got Cayman Formation, but we're not sure.
Is it that the Brac Formation is not as permeable as the Cayman Formation, where you have water of the spring coming out at the boundary?
Yeah, so the Brac, what happens there is the Brac Formation at the top would have been a very well cemented, solid sheet of rock. You get the Cayman Formation on top with the waters percolating down, and then will come out there because it's got nowhere else to go. Okay? If you go in the cave, I forget what's the big cave that's down on the east end there, you'll actually see stalactites. The roof of that cave is flat. It is the unconformity, and you'll see stalactites growing from that, the roof of the cave, because that's where the water is seeping through. Yep, you're correct. Water will always follow the easiest route that it can go. So we're now going to look at the Cayman Formation. We've got a huge amount of data on this. Over the last 40 years, we've got something like information from over 100 wells that have been drilled on the island, which have been analyzed to varying degrees. So we have a much better feeling and sense of the Cayman Formation than we do of the Brac Formation. So we'll look at what the Cayman Formation looks like. This is what the Cayman Formation looks like. white, very uninteresting when you look at it. It's deceptive. This is a very complicated formation. Just to point out, the red colors that you see in there is not really part of the formation. That's Terra Rosa that has come in later on. So this is what the typical Cayman Formation looks like. You have to get close to it. When it weathers, we lose a lot of the detail. So there's what Cayman Formation looks like. A lot of these holes, these elongate holes that you see there, that's where coral were. That's where the branching corals grew. The corals are aragonite. They've been dissolved. You leave a cavity, and then they're backfilled with the soil, the Terra Rosa. So that's what goes on there. This is an quarry on Cayman Brac. And you look at this, and it all looks the same. It really does. And plus, if you ever go in any of these quarries, be extremely careful, especially if they've done recent blasting. These walls are very unstable. So don't just go wandering into them. You've got to treat them very carefully. But this is what Cayman Formation typically looks like. The Cayman Formation has a very diverse fauna in it. Now, think back to what I told you earlier on. Most of these animals, the corals, bivalves, gastropods, all have shells built of aragonite. So what happens is, especially in the Cayman Formation, I've never seen the original skeleton of some of these animals. They're always gone. They're dissolved. So as a geologist, I then have to look at everything in a reverse sense. We have to do all the identification in a reverse sense. Anyway, the upper left is a colonial coral. Now, a colonial coral is it's a big head of coral with also many, many polyps and many different animals growing as a colony. We've lost all the skeleton there. The one on the upper right is what we call a solitary free-living coral. It's just one coral cup that will sit there in the sediment. The colonial coral on the left there, we've seen these cavities from these anywhere up to, I would say the extreme we've seen is about 1 meter in diameter. Some of these coral heads were really big. More typically, they're about 15, 20 centimeters. The solitary corals on the right, maximum size of those will be about 25 centimeters long. Gastropods down at the bottom, the shell is gone. We're seeing a mold of the inside. So imagine you take a gastropod, you fill it with sediment inside, then dissolve the shell away. So that's what we're seeing, okay? We're seeing a mold of it. One on the right is a mollusk, a bivalve shell, or clam shell as you would call it. Again, it's the shell material that's been dissolved. It makes life for us difficult because identification of these to generic and species level becomes very difficult when this is all we've got. The reason I highlight this, though, is this is the porosity of the rocks. So when you've got all these, that one in the upper left there, if you've got this big coral head that's been dissolved out, that's a huge amount of porosity. And that's going to become important. On the left-hand side, these are one of the ones that do not dissolve out. These are what they're called rhodolites. They're formed by red algae. And the red algae have a magnesium, calcium shell or skeleton. That does not dissolve. Aragonite will dissolve, these will not, so we actually see those. And then on the right-hand side, I've just shown a picture. When we're doing coring, we have to rely on what we see in the core to make an assessment of the rock. And this is what the typical core likes from the Cayman Formation. Lots of holes in it. These are all pieces of coral, would have been coral branches. In this formation, we have porosity at all scales. So we can go from caves to what I've just shown you, to here we're looking at thin sections, and we've got micropores. There are some formations we deal with in geology where you'll only get one style of porosity. In the Cayman Formation, we get all styles. And this is what makes what we have to deal with. Even to the extent that if we look at the dolomite that forms in the Cayman Formation, on the left-hand side, this is from one of the wells we've drilled on the island. I should actually have the name of the well on there, and I've dropped it off. The scale at the bottom is in microns. 1,000 microns is a millimeter. So if you look at the size of the crystals in here, the biggest crystals are about 50 microns in the Cayman Formation. The ones at the bottom, which are much larger, they're out the Brac Formation. But these rocks are formed of very, very small crystals. But even though they're formed of small crystals, if you look over here, there is a typical dolomite crystal, this rhombic shape to it. Look at this picture here. You can see the rhombic crystal, but the middle is missing. So what's happened there is the original limestones has been changed to dolomite crystals, and then waters going through it have got in and etched out the middle of the crystals. And the reason I show you, I'm not going to go into all the reasons why we get it, I just want you to be, I'm showing you this to emphasize that the porosity in these rocks is at all scales. It's at the micron scale upwards. Now you may say, well, why is that porosity so important? I've shown you one picture there. These are pictures taken on a scanning electron microscope. We would never see this in thin section. We have to use a scanning electron microscope. Significant magnification, you can see the scale bar there. But if we got thousands of these crystals all packed together and every one of them has got the middle leached out of them, that's high porosity. And the point I'm showing you, I'm not trying to complicate the situation for you. You can forget all the details. But the one detail I want you to remember is in the Cayman Formations in general, the rocks are quite porous and we get porosity at all scales. And that's really important to remember. Okay, so next we're going to go on to the Pedro Castle Formation. And again, the boundary between the Cayman Formation and Pedro Castle Formation is an unconformity. It's got huge relief on it, as I will show you afterwards. And Pedro Castle is a mixture of dolostone and limestones, very rich biota. If we do not have the context of rocks, if you just give me a piece of rock that you picked up somewhere, if I don't know exactly what the context is, it can be very difficult to impossible to separate it from the Cayman Formation. Sometimes I can, other times I get caught out. They are very, very similar. The Pedro Castle Formation, far less dolomite in it than in the Cayman Formation. Some of the Pedro Castle Formation is entirely limestone, other places entirely dolostone, and every gradation in between. It's got more or less exactly the same types of fossils in it. There's some subtle differences, but basically the same type of fossils. And also in that formation, the fossils have been leached out, so we get a lot of the same features that we see in the Cayman Formation. On Grand Cayman, we only see the Pedro Castle Formation in the area around Pedro Castle, hence the name. That's the only place that we see it exposed at the surface. If we drill on the east, so if I split the island here into half, on the right-hand half, we've never found the Pedro Castle Formation in core and drilling or anything. If we come to the left side here and onto the peninsula, if we drill down, we'll go through the Iron Shore Formation. We will go through the Pedro Castle Formation and then into Cayman Formation. The Pedro Castle Formation here, maximum about 20 meters thick at maximum. So we do find it, but the only place you can see this is around Pedro Castle itself. We'll show you this on the field trip this afternoon. So, changes in sea level. As you can see, we try and link this. Trying to link this to sea level changes is very, very difficult. One of the reasons being is that we don't have great information on how the sea levels change. We know when sea level has gone up, we know when sea level has gone down. The problem is when it goes up, it's very difficult to determine how far it went up or how far it dropped down. So when you see some of these graphs, such as the one I've shown you on the right side that's done by Vail in 1977, he would argue that some of the sea level at the end was terminated at the time when the Brac Formation ceased being formed. He would argue sea level went down by as much as 400 feet. Other papers, more recent ones, will argue, well, it only went down maybe 25 to 50 feet. And we get the same, you know, if you say, well, how much does sea level go up? You'll get a similar range. It's very, very difficult because remember, if you go back to what I told you before, we can change the situation either by land going down or sea level going up. If I hold sea level like that, I've got land like that, then the land sinks, it gets flooded. I can hold the land steady and have sea level go up, land is flooded. And if you get both going on at the same time, game over. It becomes virtually impossible to deal with. But we're fairly confident in saying about the ages of these, the Brac Formation being the Oligocene, Cayman Formation, Miocene, and the Pedro Castle Pliocene. It's difficult to be more accurate than that. I wish it could be because that helps solve a lot of problems. So, what does these Pedro Castle look like in the field? Well, Pedro Castle Quarry as it used to be. We will take you there this afternoon. It does not look like this now because it is so overgrown. I was out there on Saturday to check, and we may or may not be able to see the rock face. I'm not going to guarantee this afternoon because the vegetation has just gone wild. But in the quarry there, as I showed you before, we can see the boundary between the Cayman Formation and the Pedro Castle Formation. And right there, it's about, if I remember correctly, it's about 8 to 10 meters above sea level. This afternoon, we will take you to the Water Authority site, which is only about a kilometer inland. And at that site, the same boundary is about 20 meters below sea level. So this boundary goes all over the place. And if you think about how many people here have been up on the top of the mountain on the north side? Anybody been up top of the mountain? I mean, you haven't?
Mastic Trail?
Yeah. If you go up there, the highest point in the Mastic Trail, that's Cayman Formation. That's about 17 meters above sea level. So this boundary between here, it goes all over the place. And I estimate that there may have been relief on this in places as much as about 40 meters between the high and low end. If you go on the Western Peninsula here, the top of the Cayman Formation, anywhere right by North Sound, by the golf course up there, the boundary is about 30 meters below sea level. So there's a very rugged topography on this island at that time. So Cayman, Pedro Castle, there's the boundary. And the boundary, it took us a long time to realize what we're looking at. It's unfortunately, the photograph there is not the best in the world on the right-hand side. Got a bit blurred out. You might or may not be able to see it. But right there, you can see this structure here. That is produced by a boring bivalve called lithophage. And that bivalve is capable of boring into a solid substrate. Commonly bores into the heads of coral. These are about shells, or the shell itself is about that wide and up to about this long. They sort of rotate and rasp and bore into corals, for example. They love to do that. But they'll bore into concrete. If you've got concrete docks and that, they'll bore into that quite happily. And when you see them, it's telling you that it's bored into a hard substrate. It doesn't bore into mud. And here, this shell, the top of it, the boundary is right at the unconformity. Here we've got these little structures, or I'm sorry, I'm blocking some view here. These little structures that come up. Notice this is gray and this is white. That boundary between the gray and the white, that's the unconformity. Those little holes there, those are formed by boring sponges. So there are sponges that will bore into these rocks as well. So we know that that unconformity exists. I'm going to skip that one because we're running out of time a bit. Pedro Castle Quarry, or Pedro Castle corals. Again, notice that most of the corals, the actual coral itself is lost. It's been dissolved. We just see the molds that are left. Now, you've noticed I've said there's lots of corals in both the Cayman Formation and Pedro Castle Formation. One of the things that we see quite often in the Pedro Castle Formation is the coral that's shown on the left. And I should be able to show you this actual coral this afternoon because we'll go out there. Corals are very, very sensitive to the environment, really sensitive. So if you have a coral, it doesn't like having mud around sediment, because what happens, the coral sits there, mud goes on it, it literally buries and the coral can't function. So if that starts happening, you've got one of two choices. The coral either dies or it does something to do it. This particular type of coral that is shown on the left-hand side is what we call a free-living coral. It's localized and it liked to live in loose sediment, because if the sediment came on, it was capable of moving itself up to the surface. This type of coral is very, very rare in the Cayman Formation. I think we've only ever found one or two of them. Pedro Castle Formation is full of them. So it's telling us the biota's changed, the seafloor changed, and that's one of the differences we see, which is good, because if we find that type of coral, it helps us identify that we've got Pedro Castle Formation. If we look at the Western Peninsula here of Cayman, going from the south to the north, at the north end we stop at Hell. Hell is Cayman Formation. And we do see some of the Cayman Formation isolated here. But you'll notice that what you see there, this is the top cross section, it's like a big basin. and it's partly filled with the Cayman Pedro-Castle Formation, and then infilled by the Ironshore Formation. So again, emphasizing the fact that during its history, this island has had some fairly rugged topography. It's not the flat island that you see now. And that we will see this afternoon. So for example, PCQ, Pedro Castle Quarry, that's one I've just shown you with the boundary that you can see in the cliff face. When we go to the Lower Valley water site where we did drilling, where we show you this afternoon, look where that boundary is now. So that boundary comes down, and now we're about 15 meters below sea level. And that boundary then goes up again, and of course this is, if we projected that line across, we would be just about at the mountain on the north coast, where that boundary is 17 meters above sea level. So if you'd have been here at that time, you'd have had a lot of topography to deal with. This one will make your head spin because there is so much data on it. And the only reason I show this is to demonstrate to you that the work that we've done and what this is based on very detailed work. So on the left, for example, we show the crystal size of the well. This is the Lower Valley well. We're showing the amount of different types of dolomite. We're showing the ratio. So everything we've done here in these wells is based on thousands of analyses. So if you look at this, every dot on there is a different analysis. So this is based on quite solid data. I wonder if this, let me do it. Okay, just to emphasize this, this is a three-dimensional view of the topography of Grand Cayman today. This is based on the Lands and Surveys data. The black, the dark colors are the high points on the island. So you can see here, Pedro Castle area, that's the mountain. And in case you're wondering what that peak is, that's the rubbish dump. Okay? And what you can tell from this is that if you look at this, we've got high land on the east. Notice that on the east end of the island, there is a ridge that goes around the island. There is a distinct ridge all the way around it. So that's what the island looks like today. But if we take all the data that we've got from all the wells we have, and I'm the first to admit we don't have this perfect because we don't have enough wells. So we have to do a bit of extrapolation in between. But you can see from this that topography about 5 million years ago, which is roughly the boundary between at the end of the Cayman Formation, North Sound was there, but it was way deeper than it is today. You had the same ridge. Going across the island, the east end was still the highest area, but you had lots of low-lying area. And we don't have enough data points to show precisely every areas, but in the modeling we use to do this smooths things. So you got, but probably in between Pedro Castle and going to east is probably much more rugged terrain. But it gives you an idea of how things have changed. Just let me do a quick. Do we want to do a quick break now? Or? Okay, sorry, I'm just debating whether I give you more lectures and send you further asleep, or whether you want to. I think, though, we'll take a quick break. Okay, so what we're going to look at next is the Ironshore Formation, probably the one you're most familiar with because you find it all over the place. It certainly is a very interesting formation from a geological point of view. Very rich biota of corals, bivalves, gastropods and other things. So, and plus it's relatively easy to work with. One of the things that you have to understand here is during the last 800,000 years or so, and especially during the last 400,000 years, which encompasses most of the Ironshore Formation, the sea level has been going up and down like a yo-yo. So think back to the principle, basic principle, it goes up, you get deposition, goes down, you get erosion. So in the Cayman Formation, we've now identified 6 different units in the Ironshore Formation. These are called members, technically. So a formation we can divide into members or units, whatever you want to call them. And each of those we can tie back to when there was what we call a high stand of sea level. So if sea level goes up, we call it a high stand. If it goes down, we call it a low stand. And these have been tied back quite well to fluctuations in the amount of ice in the polar ice caps. So if you get the ice cap from the South Pole starting to melt, sea level's going to go up. If it expands, sea level will go down by significant amounts. And for example, over recent years, when we've had the ice cap on Greenland melting at a phenomenal rate, we're seeing that impact on the sea level going up. And yeah, you say, well, it's only a couple of centimeters a year. But remember, in geology, we're dealing with tens of thousands, hundreds of thousands of years. So this makes a significant change. So each of these, what we call high stands in the Ironshore Formation, gives us a different sequence of rocks. And these are divided into A, B, C, D, E, and F. Very original lettering on it. But one of the advantages we do have for this formation is that when we've got shells that have got their original aragonite skeletons, we can use what we call uranium-thorium dating. We look at the ratios of the uranium to the thorium that's in the shell material, and from that we can calculate the ages of these fossils fairly accurately, or we think they are. So we can put some ages on these. So we're going to look at these. Now, I should point out to you that members A, B, and C do not outcrop at the surface of the island. We have never found these in the surface. The only place we found these is in some drill core that we got from the northeast corner of the island. D is widespread. That's the most common element. E is very rare. The only place we've found member E is some years ago, there were some wells drilled off the west coast of the island here. They actually drilled them into the seafloor and down, and you find member E, that's the only place we've seen it. Member F is, we find it scattered places on the Western Peninsula here. Most of the Ironshore Formation you will see will be Unit D. And that was deposited about 125,000 years ago. And we've got good dates on that. So, and one of the huge problems we have with the Ironshore Formation is that in most cases the Ironshore Formation is so poorly cemented, we cannot drill through it. Well, we can drill through it, we just can't get core. So if you're on the Western Peninsula here, wells have been drilled here. I've never seen a piece of core come out of one of them. We've tried it with some of our rigs. I've seen the professional drillers try it. The rock is so friable that the drilling process destroys it. The only place that we have been able to get good core is up on the northeast corner of the island, Rogers Wreck Point. And then at that time, many years ago, if you look at the left-hand side, this was a portable drilling rig that myself and my students used to use to get core and drill on the island. And if you look on the top right-hand side, where we did a series of cores going across there, and the bottom shows you the cross-section based on those cores. It just so happened in that area, the iron shore is well cemented and we could core it. We got fantastic core. Everywhere else we tried, never one piece. So when you look there, what you will see, if you go out there and look at it, we won't see this area today. We don't have the time to do it. If you're driving along the Queen's Highway there, on the inland side of Queen's Highway, there will be an outcrop of the Cayman Formation. You'll see a wave-cut notch there. That wave-cut notch is 6 meters above sea level. Remember that figure. And then as we do the drilling, we find that the surface of the Cayman Formation drops off like that, and then we get the iron shore units deposited on this as sea level rose. So you gain an illustration of the complexity of the effects of sea level changes. The core, we were so lucky to get that because otherwise we would be still struggling trying to understand the iron shore formation. That is the wave cut notch that I just showed you. In the original, I will tell you now, in the original itinerary for the field trip this afternoon, I was going to take you and show you that notch. When I went there on Saturday, I had trouble finding the vegetation is so dense, so overgrown. I could think I found it, but if I took you there and show you, you'd laugh at me because it's, you know, you'd have to be using imagination. So I'll just tell you now, we won't go there because of that. And this is what the iron shore formation looks like. There are some beautiful exposures around North Sound here, where you can see the units D and unit F here. Beautiful limestones, full of fossils. Don't ask me where the little truck came from. Many years ago, I used to run field trips down here for my students from the university. And why, I don't know. One of them happened to have this truck in his pocket. And next thing I look at the outcrop and there's a truck with a bivalve in it. Only students could do this, you know. So, but anyway, it gives you an idea. I like to use it and say there's truckloads of bivalves in it. So, but this gives you an idea. Look at the density of those bivalve shells. It's just crammed, all perfectly preserved. These are all aragonite shells. They're perfectly preserved. These are 125,000 years old. Not in this one, but there are other places on the island I've done. They still have the original color of the shell on the outside. It's amazing. But, you know, these are so old, and yet they're so perfectly preserved.
Question, you said those are aragonite?
They're aragonite, yes.
So is it that they have not been exposed to like fresh water?
Absolutely. That's probably the reason why but in a sense it makes no sense because we know after Unit D there was a drop in sea level, but for whatever reason they never got affected by the fresh water. They got preserved. I mean, we've pulled out conch shells that have still got their original colors on them. So that's how well preserved they are. And that's why I say when we've got shells like this what we can get uranium, thorium dates from it, and we can treat them with certainty because we know the shells haven't been altered. So beautiful preservation. Yeah.
What is it about the fresh water that actually, is it a different pH or something? That
Yeah, it's a different composition. It's that simple. If it's bathed in salt water, the salt water is not aggressive, because remember the shells grew up. They grew in the salt water. That's why they've got aragonite. That's the stable shell. As soon as you change that and put fresh water, remember, fresh water can be slightly acidic. Aragonite is more reactive than calcite. So you will get that dissolution go through. So that's what the issue is. So if you imagine we took those shells and put a box around them and we didn't allow water to get into them, they're preserved. Now, if you're looking, especially for teachers, if you're looking for places to take students to show them fossils, this is on the northeast coast where where the boat ramp is up there and that stretch of coastline up there. This is an incredible exposure of the iron shore. In previous years, we've actually taken you to this exposure to show you. I'm not doing it this year because last time we did it, we ran into so much trouble with traffic when we was trying to get back to look at some of the outcrops on the south coast. It just killed us. So I've got to stay away from that. Okay, but this, if you want to take students, show them, this is a relatively safe place to do so. I mean, it's never, I'm not going to say it's perfectly safe, but it's, and the reason it's so nice is that you may as well be walking along the seafloor as it was 125,000 years ago. The corals are still in the position in which they grew. So if you look at that big coral on the right-hand side, which is a big colony of Diploria labyrinthioformis, that colony is about 1 meter high. It's perfectly preserved. It's still got its aragonite skeleton. It's just sitting there. You look on the left-hand side here, you can see all the branching corals that are still in growth position. When we use the term growth position, we mean that's where they grew. They have not been moved. These are 125,000 years old. Perfect. So if you go up there, you're essentially walking across the seafloor. This afternoon, I found that we've got another site at the Dart Family Park by the National Trust. It shows you exactly the same thing. It's not quite as good as this, but it's for a trade-off in that. So this is what the iron shore often looks like. One of the questions that always comes up from geology point of view is, okay, how high was sea level when these units formed? Very difficult to really get accurate figures on them because it's one of those invisible things. How do you go, if I took you out and showed you these corals and said, okay, how high was sea level when they grew? You'd look at me and go, don't know. They grew in the photic zone. Photic zone here is anywhere to 120 feet depth. So you've got all sorts of problems. But these give you an idea of the different water depths. So for units D, E, and F, sea level was about the same in high, and you had low levels in between. So it's just sea level bouncing up and down. We get a bit of complication on Cayman Brac. So I finished dealing with the iron shore and that, but we're now going to start looking at the, where is that? Just a minute. Yeah. We're now just going to look at some of the issues, other issues we've got to deal with. Hopefully now everybody, I know I'm throwing an incredible amount of information at you with all sorts of strange terminology. I've tried to keep the terminology minimal, but sometimes I can't avoid it. Is everybody comfortable with what I've dealt with so far, or does anybody have any questions at this point? Because I'm going to change the theme here a bit. Yep.
What underlies carbonate rocks? What formed the original mountain range? Is it
That's
volcanic
Really good question. Really good question. I can't give you an accurate answer, and the reason I cannot do it is that we've not yet had a well drilled that's gone deep enough. In the early, when was it? Early 70s, there were, I should know that date and I forgot. Early 70s, there were 2 wells drilled on the island here. One well was on the south coast near Bowden Town, and the other well was on the Frankstown Road, getting up towards Old Man Village. They were drilled by an oil company and a local resident because they wanted to see if there was any oil reservoirs on the island. The deepest one of those wells went to, 400 and something feet. Okay? Unfortunately, the descriptions from those wells are very poor. We've tried to find the samples. We've not been able to find the samples. But going based on what the poor descriptions are, that was still in limestones and carbonates at about 400, 450 feet. Okay. There are records of people that have done deep dives off the south coast of Cayman that seem to indicate that the carbonate rocks go down to at least 600 feet. Then it gets very hazy. Beneath that, we do get into volcanic rocks.
Yeah.
So the simple answer to your question is the carbonates sit on top of volcanics,
Yeah.
but we don't know exactly at what depth. I wish I could. The problem we've got here is the drilling rigs that are on the island.
Yeah.
We've already pushed those. We've pushed them to the limits. We've pushed them to Lower Valley. We got one well down to about 420 feet. And that was literally almost at the breaking point for the drill rig. Most other cases, we can only get drilling done to, 200 or 300 feet. The equipment's not here to do it.
So in theory, there would be volcanic rocks and then erosion and
Yep. Yep.
deposition.
Yes.
All the way up
Oh,
that.
yeah, yeah. So that's the best answer I can give you on that. Next thing that adds to the complication here is that as best we can tell, and I have to preface this, the rocks here on the island are flat lying. In other words, they're sitting there like that. Their attitude has not changed from when they were deposited. When we go to Cayman Brac, the situation is different, of course. Couldn't be simple. And you go on to Cayman Brac, that has been tilted up. So the east end of the island has come up, the west end of the island's gone down a bit. The best we can work out, because this really gets very difficult to, we think this took place. We're a little unsure whether we took place before deposition of Pedro Castle Formation or after. Because again, it's like, so if, just think about it in practical sense. If I put my glass case on the floor and you left here tonight, you came back in 5 days' time and it's on the desk, how would you tell when it went up? You couldn't tell. So we have the same problem with geology, except on a scale of millions of years. And that's where we run into trouble. We think now, on somewhat dubious evidence, that the tilting of that island was probably before the Cayman Formation, but we wouldn't be surprised if we came back later on and said it's after, because we're still trying to fight with that. The other problem we've got there is that on that diagram I've shown it steep like that, just so you understand it. In practice, it's about a 1 to 2 degree dip, so it's a very subtle thing. And remember, we've got karst topography on top that makes it even more difficult. But this also then complicates correlation between Cayman, Brac, and Grand Cayman. Little Cayman we don't know because there's never been a drill. Water Authority is supposed to drill a well over there. They're having trouble. Nobody wants to go and drill a well there. That's what the issue is. I don't know why. I'd go there and do it. Okay. I'm going to show you a piece of core. This is a sort of a classic piece of core. This is from one of the wells on this island. What do you see there? Why do you think that's important?
Cavities.
Sorry?
Cavities.
Cavities. So why are the cavities important?
Well, that can help in terms of NI, where we can send water in.
So you can send water in.
For drainage.
Yep. Water Authority can take water out. But you're all wrong. What I see there is money. And the reason I see money there is because in some parts of the world, that's where the oil would be. Here it would be where the water is, so you're partly right. That's where gas can be. That's where mineral deposits can be. So this is why the porosity is important. That's what houses these different things that are of value. So certainly here, as far as we know, there's no oil, there's no gas, there's no minerals deposited. So this is purely a water issue. So with Apollo, you are correct. That's where you can send the water down. That's where we can take water out. But I want you to understand that that rock is important everywhere you go to. You know, the oil, the gas that you put in your car ultimately comes from rock like this. So practical application. Water. You all drink water here, so now we're going to see what happens. So this is and I apologize, I should have put the credit for this photograph on here. It's not one of mine. I tracked this photograph down for the book that I've just finished. And this is the traditional, or one of the traditional ways of water collection on the island. You've all seen it. You know, you've got the rain coming off the roof, you've got the pipe going across to the cistern, or the pipe goes into the basement, and you do that. So that's the old way of doing it. And of course, that had all its associated problems with it. So as the population of these islands have grown by incredible amounts recently, then the issue of drinking water becomes more and more important. And on Grand Cayman, you've got three main water lenses. You've got the East End lens, North Side lens, and the Lower Valley lens. On Cayman Brac, the main one is the Tibbetts Turn lens, and then there's some smaller lenses that are used locally. On this island, at present, Lower Valley lens has been developed and the East End lens has been used. North Side one is big, but it's awkward to deal with. That's where you've got the ridge of dollar stones going along the north coast. So anyway, it's not been developed as yet. So these become important. And just to show you what one of these lenses would look like, if you go into Crystal Caves, many of you have seen this, perhaps seen this underground lake. That is actually the top of the North Side water lens. That's the freshwater lens. You're actually seeing the top of it. It's spectacular. I don't know anywhere else where you can do that. And it's great, because then you can get in there and take water samples and all sorts of things, which we've done. So that's what it's like. So one of the reasons I've had a long association here with the Water Authority, to date myself here as to how long I've been coming down here. I was here when the Water Authority was first formed. The initial staff level of the first Water Authority was 3 people. There was a director, a hydrogeologist, and a secretary. And they worked out of a house by the hospital. And you look today at the Water Authority, it's 145 people employed, and you see all the facilities. So I've seen, I'm dating myself here, of course, but yeah, it's grown a little bit. Water Authority then expanded to 4 or 5. One of my PhD students came down to work on the water lenses and to characterize them. And then 1993, I get a phone call from Hendrik van Genderen, who's not here today, saying, we've got a problem we want you to solve. We need to further develop the Lower Valley water site. So we need you to look at the geology. We need to get a well from at least from which we can abstract 10,000 cubic meters of seawater per day. You cannot damage the existing freshwater lens. You cannot damage any vegetation on the surrounding land. And what I have to explain here is that prior to that, the Lower Valley lens was a major source for drinking water. So you'd get, trucks would go and get the water and take it out. Problem with that, it wasn't being regulated. So the lens was being damaged. Because you've got balance. If you take too much out and you haven't got enough rain, then it doesn't balance it. So the idea was, this was one of the first sites where they put the reverse osmosis plant in which you take seawater and transform it into fresh water. You'll see this afternoon. And when you do that, so we're inland. You can't put these plants on the coastline. A, because the coastal land is so expensive, and B, we're going to actually produce an offset of this. You produce seawater that's even more saline than it is now. If you put that directly back in the ocean, you'd kill every coral in sight. You can't do it. So this is why I got this list of conditions. I looked at this and said, eh. Anyway, so what we had to do, and what you have to remember here, as it says at the bottom, for every 10,000 cubic meters of seawater that you pull in, you produce 4,000 cubic meters of fresh water. You produce 6,000 cubic meters of brine. So you've now got to get rid of the brine. So you've got to take salt water out, process it, put the brine back in, but you can't have the two interfering. So that was the challenge we had there. And in those days, 1993, we did not know as much about the geology as we know today. One of the reasons we know more about the geology today is because of this well. And there's the drilling rig, there's the core. We spent many days at the site while it's drilling, making notes and getting bored out of our minds because sometimes the drilling is not very fast. And eventually we came up with this scheme. So if you look at the top, there's the freshwater lens and the shallow strata. We had to preserve that because the local people around there, that's their right to still use the freshwater lens. And if you go and destroy it, we would have to leave the island. So that had to be preserved. And you can damage that lens so quickly. It's very easy to do. And then we had drilled through the Pedro Castle into the upper part of the Cayman Formation, lower part, and we actually did detect the Brac Formation in there at about 400 feet. The thing that saved us, and what the key here is, was the geology here was such that, if only that pointer would work, we have what we call a cap rock. Now, so just bear in mind there, all right? And then when we get the core pieces out of there, we can measure the porosity. The porosity is the percentage of pore space in the rock at all scales. And then we can also measure the permeability. Permeability is a measurement of the ability of a rock to transmit fluids. So how easily can this fluid move through the rock? It gets more complicated, and we can't just take, so if we take a piece of core, we have to do 3 measurements. We do permeability in the direction of maximum permeability. We do another measurement at 90 degrees to that, and then we do vertical. And we have to do that to characterize the rock. It gets further tricky because when you're doing those tests, you cannot have any holes that go through the entire width of the core. You can't have any fractures that go through. It's all sorts of issues. So this is the best we can do with it. Now you notice in that cap rock, the porosity is very low, about 10%. Permeability is very low. And that was great news, because that, in effect, was a seal. That was a seal. And then you notice underneath it, we get that, look at the permeability, the porosity levels and the permeability. Look at the porosities. Theoretic maximum porosity you can get in a rock is about 49%. Because think about it, if you've got rock with holes in, if you take too many holes, it's just going to collapse. So the theoretical maximum is about 49. In some of these, we're up in the range of 47, 48% porosity. It was amazing. And then we got the zones with high permeability. So at the end of the day, we've got the abstraction zone there, disposal zone there. Those would be in 2 different wells that are separated with a couple of 100 meters between them. And that's the design that Water Authority came up with based on what the geology we gave. That was in operational since 1993. There's been a few times when it's been down for that, but basically it's still operational today. Is it still producing the same? Yeah. So it's still producing the same volumes of water.
These characteristics, do they change from one freshwater lens to another?
Yes.
Significantly?
Yes. Nothing on this island behaves in, I mean, one of the reasons I'm still here looking at it, beside the fact I love coming to the islands, is the geology. The more we pick at it, trying to, as geology, we keep on going at things, hoping that we can get a good sense. If anything here, I'm going backwards, because the more we know, the worse it gets. So we've done that well. We've done the same thing with, we did the same process on the north side well, which is biological. Totally different. Same formations, totally different behavior.
Try to explain that to a civil engineer. I said drill to 100 feet minimum. It's about this one. But the engineer figured it out.
Yeah, but so for example, on the north side well, it was totally different. They had to bring in a special rig from the States, and we ended up, I think the abstraction down there is about 600, 700 feet down, I think, isn't it? 8. That's how far we had to go. And that gives you an illustration of how this changes. This rock, it may appear to be layers, and they are, but it changes so much, and it causes massive headaches.
We know that
Yeah, you'll know that from the road.
50 feet apart is a big difference.
Sorry?
50 feet apart between
Yep.
wells.
Yep. Yep, that's what. But anyway, thankfully for me, if that hadn't worked, I would not be back on the island again.
Is it the low permeability, vertical permeability in the disposal zone that means you don't need to have a buffer zone?
Yeah. One of the things we've still not solved and we don't understand is that some of these rocks have very good lateral, but they have poor vertical. And we have looked and tried to, we can't figure out, intuitively you would say, well, if you've got good permeability that way and this way, it should be good this way. It makes no sense, but we haven't been able to solve it. So I can't give you an answer to that.
So Freshwater lens doesn't necessarily have, it's not a full cavity, it can be raw.
Oh, no, 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 that,
That's
I
a
mean,
misconception.
that's a total misconception, all right? There's not just a big cavity underground. All that fresh water sits in all the little holes there. Now, of course, I ruined that because I showed you the picture of the north side one where you can actually go.
And there's other place like, I don't know, Ventnor Cistern where there's have you been there, where it's like a tunnel down?
Yeah, and of course that's,
Very cute.
you can go into Bermuda, I've been there, and yes, but here, no, all right?
Yeah.
So anyway, so there's the practical application of the geology. Thankfully, it's still going, so I can still come back to the island and visit. So 1998, it produced 1,500 cubic meters of drinking water a day, and then it's gone up progressively. And 2015, 4,500 cubic meters a day. So it's still handling. So that's been a success story from the geology. And of course, the problem you've got, and I know the Water Authority has it, is if you look, these are the graphs. Now, these graphs are for Grand Cayman. That's total water production from all 4 of the reverse osmosis plants. So there's 2 here in Red Bay, 1 in Lower Valley, 1 in East End. But look at the climb and the production needs. Cayman Brac's not so critical, but this is a reflection of the population numbers. So if you look at the population numbers, which I've just tracked down, 1802, less than 1,000 people. And you go up to 2006, 52, and in the last preliminary results of the last census, nearly 70,000. Sorry? 78,000 now? Wow. So there's the driving force. Just think of how much water you need. So take it back to Cayman Brac. I'll show you some Pacific features. Cayman Brac on the right-hand side and Puff Cayman on the left. And remind you, these are the geological ages we're dealing with. So we're going to start here on Grand Cayman, start with the Iron Shore Formation. And I've shown you this already, showing you this again. We won't see this one this afternoon. I've substituted because of the traffic. When you see the Iron Shore Formation, it's about 15 different species of corals that we've identified in the Iron Shore. Many of them are the same species that you see in the present-day ocean. So literally, if we go to these, you're going to be walking over the seafloor as it was 125,000 years ago. And you're going to see the same, use your imagination, you'll see the same corals that you would see if you were in the present-day ocean. And there I'll show you those again. Just in case you wonder, okay, what's your evidence for the changes in sea level? Well, when you get, this is on the north-east corner of Cayman Brac. There are some outcrops of the Cayman Formation. If you look on the left there, you can see that you've got sort of mushroom shape. And this indent at the bottom, this is what we call a wave-cut notch. It's formed by, it's not just tidal action, it's animals living there and burrowing into rock, so it cuts in. On the northeast corner of Cayman Brac, there is that one outcrop shown on the right-hand side. You can see that other wave-cut notch, that's 6 meters above sea level. And we know that that's the one that formed 125,000 years ago. Okay, so we can see that very nicely. We can see this, we will see this one this afternoon. We can see the wave-cut notch at Old Man Village. And then on the right-hand side, I'm showing you a picture of the south coast of Cayman Brac, where you get this incredible in-cut. I mean, it's really deep in there. You won't see the wave cut notch on the east end of Cayman Brac. The simple reason, think about it, you cut underneath and you've got all that rock above it, it just collapses, so you've lost it. But on the west end, there's not so much rock in there and you get this big cut in. So we'll look at some of the Cayman Formation. We're not going to Hell because of traffic. I'm going to show you an equivalent site, not quite as spectacular, but you'll get the idea of it, not far from Pedro Castle Quarry. This is what, you all know Hell, this is why it's called phytokarst. Phyto meaning life. In older literature it was called biokarst. So phyto is just a bit more fancy. The rocks here are Cayman Formation. If you broke open these, they would be white inside. The grey coating is created by all the microorganisms, the algae, fungi, all those things. They like to live on the rock. They have the ability to bore into the rock. Despite how hard it is, they'll do that. And then as those organisms die, so that gives the grey patina to the rocks. You can see that all over the island, but it's just that Hell is, I mean, my favorite one, I went up to Hell once, and this is where as a geologist you have to be careful because, anyway, I was up there and there was a taxi driver with a group of passengers and he was explaining to them the origin of this. And he said, oh, it's volcanic material. It's an eruption. And one of his passengers said, well, okay, well, where is the volcano? Oh, that was North Sound. So just be aware that you can get some crazy interpretations on this. And if you look at it I don't know how many of you tried ever to walk across this stuff. If you're going to do it, be extremely careful. The edges on these rocks are razor sharp. They will slice you open in a minute. So if you slip and your ankle goes down it, you're in trouble. I've so far managed to avoid doing that. I've had a few scrapes from it, but just put it this way, for the teachers here, don't take your kids out on this. I guarantee there'll be a major problem. So plants here help on this. So on the right-hand side shows you this at the east end, where these trees have rooted right down in the rock. And it's incredible. They'll go to great depths in the rock. You can go into the caves, on the crystal caves on the north side, and you'll be in the caves and you'll see the roots coming out of the roof of the cave coming down. So they're quite capable of, through their processes of etching and widening and penetrating these rocks, which also goes into the issue of the phytokarst. But these are scanning electron microscope pictures. Notice the scale bars on the bottom, 50 microns long. Look at all the holes in there, and in this case, right here, and a few places there, those are actually the microbes that are preserved. They're the ones that generated those holes. So these algae, fungi, and bacteria, they are quite capable of boring into these rocks. And if you get enough of them, that's what they do to them. So that's part of the weathering process. So changing in sea level, Pedro Castle Quarry, we'll see this afternoon. I'll go through these quickly because I'm just putting them in here to remind you. There's the Cayman Formation, Pedro Castle Formation, and again, caveat, you may or may not be able to see this afternoon, when we went to check this on Saturday, we couldn't actually get into the quarry itself because the gate was closed. We're hoping the gate will be open for us this afternoon. And just put your minds, we do have permission to go in there. You cannot go in there without permission. And the reason being is at the back end of the quarry, they store all their explosives that are used. So you have to get permission. You can't do that. So now, I've shown you this one before, but again, it emphasizes the change in topography from the coastline out to the area. Forget that one. Okay, sorry, those other two shouldn't have been there. I've had major computer problems. I got down here on the island, my computer decided it didn't want to behave nicely, so we've got a little bit of a mix-up here. After we've been to the quarry, we'll go out to the coastal area, right by the Pedro Castle site. And what we're going to look at there are a couple of different things. We're going to look at the corals that you see in there. They are different from the type of corals that we see in Cayman Formation. These are these free-living corals. Not always easy to see. I'm hoping they're still visible. These are on some of the pathways, so they may have been worn out by now. We will then go out to the east end. We're going to look at these boulders. For those who know the East End, when you get the road that's coming south from the quarry, the High Rock Quarry, right opposite that is a stretch of coastline. That stretch of coastline, there's no offshore reef, so it gets the full force of all the storms and hurricanes. And in this area, many years ago, we mapped all these boulders. There's 52 different boulders. Including this one here. This one here is about 3 meters long. It's about 2 meters wide and 1 meter a bit high. We did some crude calculations. We figure weighs about 10 tons. And yet the evidence is that this was moved here by a storm. And if you look at the right-hand side of it, you'll notice that it comes flat and then it arches around and comes like that. It's the profile of a wave-cut notch. And the interesting thing is we've found a few boulders there with the same thing, and in every case that is pointing to the east. I have no idea why they orientate them that way. We did go out there on Saturday, check that vegetation is a bit heavy there. So I probably, plus because my hip problems, we're not going to be able to see all the boulders, but I can certainly show you some of them, okay? It's a fascinating place to look at. This is actually a map. All those black dots show the positions of the boulders. That area, as you see, is divided into two zones. Zone A is a bit lower, Zone B is higher, and when you come to the boundary, so Zone A comes like this and then comes up to B. So we think that may have been the coastline 125,000 years ago when sea level was 6 meters above where it is. We've mapped in, all the black there, mapped in positions of the boulders. There are boulders to the north of the road, on the northeast side of the road there. We have not mapped those in because it was quite evident that some of them have been moved by building, road construction, building of the church, and other things, so we didn't. But there are boulders there. But the conclusion we came to on this was that these are all moved onshore by a massive storm, massive hurricane, possibly a tidal wave or something. If you get landslip in the ocean offshore, you can generate these huge tidal waves that come in and move these. Must have been one incredible storm. We've dated some of these. We think we've got some problems with the dating we've now discovered. We think this happened maybe about 300 years ago. There is no historical record of this on the island. So this almost certainly predates first settlements. So we'll see those this afternoon. And the histograms at the bottom show you the lengths of these boulders in meters. They're big boulders. And what was really interesting is that one of the smaller ones, I say smaller ones, you wouldn't be able to move it, I couldn't move it. After Hurricane Ivan, the boulder we went back there and the boulder had been turned upside down. And we think that has to be from Hurricane Ivan. And the reason it happens there at the coastline, there's no offshore reef. So it gets the full benefit of these waves. We've found exactly the same thing at Pedro Castle Quarry. So if you go to Pedro, let me go back. Yeah. If you look at Pedro Castle, so we're standing on the pathway, there's that house there. If you go along the coastline past the house, you'll also find boulders strewn across the shore there. And again, this is area, no offshore reef. So you get full force of the waves coming in. Yeah?
You're familiar with the Savannah Gully?
Sorry?
You're familiar with the Savannah Gully, which would be a little bit to the west of that?
Yeah, I've heard it. I've never actually seen it.
See that?
No.
It's subtle there, but
Yeah.
water comes on shore there.
Yeah.
It's
Yep.
about 6 feet or 6
Yeah.
14 feet.
So you could easily do it.
Well, yeah, every time it's floods, the elements will flow like gallons.
Oh, yeah. Yeah.
But
Uh,
I understand also offshore, the pond is also different steps up.
Yep. So anyway, it's another interesting aspect of the geology. So we've seen that, go back. Yeah. This is the boulder I was talking about. On this particular boulder, the rock type is from the Cayman Formation. It's the dolostone of the Cayman Formation. But on this particular one, there were corals growing on the surface. There were borings in it. So if you see on the lower part, the corals, those are the ones we originally had dated. They were originally dated at 660 plus or minus 1,000 years BP. So that gave us an age of 1862. We've discovered some problems with the dating. The carbon-14 dating is not easy and straightforward as it seems. You have to make a certain amount of assumptions, and we've discovered that perhaps some of those assumptions were not correct since we did it. Anyway, but it's that boulder which we went back to after Hurricane Ivan and found that the corals that were on top were now on the bottom. And we looked around, there's no evidence of mechanical movement, but we also found other boulders where we could see them, and you could see drag marks across the rock surface where they'd been pushed across. And again, no indication of mechanical. There's no reason anybody would do it. We calculated roughly that those boulders were moved 5 to 6 meters vertically up and 100 to 150 meters inland. I would not want to have been there when that wave or those waves came in on this. Caymanites. We're all familiar with Caymanites. Some of the beautiful carvings that are done on it, and the question is always, how do you form Caymanite? And of course, there's all the mythical tales of how it forms and that. Caymanite's a bit of an enigma. It took us a long time to sort this out. Caymanite is, as you see, and you know, it's multicolored, everywhere from white to red to black and everywhere in between. And typically, you find it inside cavities. So on the right-hand side there's a coral that's been leached out, Caymanite deposited in it. One of the great problems we had in trying to explain that, what I show you there, that's fairly easy to explain. It's just sediment being washed in. Red is because you've got iron coloration. Black is because you've got manganese trace elements in it. So you can associate the colors with different trace elements that go into it. But one of the problems you have with this is, and again, there's a beautiful piece there, but in other outcrops you look at, and the laminae on these things are going at this angle, that angle. They're all over the place. They make no sense. Sediments should be laid down flat. Very rare that they've got these angles to them. So in part what we think has happened is, think of storms. So you get something like Hurricane Ivan comes through, it's moving all the sediment around. So if you see on the top pictures, this is the east end of the island, top left. The road is on the left-hand side. That sand-covered stretch is the road. That's come out of the lagoon and from the beach and is being brought in. That can also be taken any distance inshore. The one on the right is from Cayman Brac, and these just show it. But the idea is if you've got storms, it brings all this sediment in. As it's bringing the sediment in, it's also picking up stuff from the swamps and everything else. Because if you just put sand in there, it should all be white, so why have you got black and red? So basically what we're looking at here is sort of fair weather conditions, storms bring the sediments in and depositing them. And one of the problems we had with this is when we'd look at outcrops of the Caymanite, you'd see on one side the Caymanite layers are dipping this way, other sides dipping this way, they're dipping in all directions. And that puzzled us for many years. Some years ago I was very lucky when I was wandering around the coastline at Pedro Castle Quarry, I came across these deposits. Those cones, those are Caymanite. And if you look at the very top of them, you see here and there, you see they go up. And what that told us and allowed us to interpret it made sense, because you can actually model this. I did model it. If you got a hole, got a cavity, you have a hole in the top, you bring the water and the sediment in it, it comes down in the cavity, it goes down and then flows out in all directions and deposits the sediment. And that's what's happened here. This is where the Caymanite formed, so you get these cones. And that's why when we used to see cross-sections through it, we saw it going in every direction. Because you imagine you have a cone like that and then do random vertical cross-sections, you're going to see things dipping in every direction. Caves, magnificent caves on the island. This is one near Old Man Village that we used to go into. This is on private property, so it's not, again, not open to the general public. But beautiful caves with stalactites, stalagmites. This is where you get calcium carbonate precipitated. We get terra rosa being brought into the caves as well. In some of the pools that used to exist in these, you get these round structures. They're called oncoids. These are, imagine if you took my glass case in, you get covered in calcium carbonate precipitate. It then moves, so the bottom gets just successive layers. And you do get various microorganisms, fungi, algae, well, fungi especially, that like to live in the pools, and they help in the formation of these structures. If we cut cross sections through these, you notice the one in the top right corner there, that's a piece of bone in the center of it. It's probably the bone from we think either a bird or a rat or something like that, because you do find it. And they have been in the pool and get coated. Beautiful caves. So these are caves on some of the caves on Cayman Brac. So visualize what I've shown you before of the Cayman Formation. You get caves, and now we're starting to fill the caves with more sediment.
Is it from the meeting lines of two different rock types, or is it just water cavities?
Just water cavities.
Eroding
Yeah.
from seawater over
Yep.
rains?
Seawater, fresh water, He formed in the caves. Obviously, they probably formed in times when the climate was much wetter than it is today, where there have been vast quantities of water going through.
We've been trying to map DOE, a lot of the caves, but certain areas like the mountain, we haven't found any like large caves. But other areas we find.
Well, I get frustrated because I go into these, and as a geologist, I want to collect the water so I can get it analyzed to see what's precipitated. And most times you go in the caves, there's no water.
No, dry.
I've managed it once on Cayman Brac. We went in some of the caves about 3 days after a heavy rain, and then we found some dripping water. So I ran around like a mad fool collecting all these water samples.
Not many of them are active.
No. But when you look at caves like these with these beautiful, I mean, at some part in recent history, there have been a lot of water flowing through.
And then there's also, I know the water lens isn't a big cavity, but there's potential for submerged caves as well.
Yes. Oh, yes. Yeah. Yeah. Terra Rosa, red soil. Red, I think it's known as red mold is the local name for it. You see this all over the islands. Okay. This is one of the latter projects I did because I had too much other things to do, but it's always fascinated me why these red soils are here, where they come from, and how they developed. So we will see some of these when we're out today. They're literally red soil. They do get lithified, so that they become very hard rock. They are, oh God, that's a terrible slide. Jeez, I must have had my binoculars on. I apologize for that. Very complex from a mineralogical point of view. So we've got, let me put my glasses on. I'll apologize. I usually have these much clearer than that. So we've got silica, SiO2, Al2O3, iron, Fe2O3, CaO, titanium oxides. LOI is loss on ignition. So when they're doing the analysis, they will fire it first to get rid of the combustibles. And then P2O5, that's phosphate. So these are incredibly complex from a mineral point of view. I won't even show you the mineralogy on these. They've got about anywhere up to 15 different minerals. And I have to admit that I got the analysis back, and some of them I'm looking at, I had to go back to my mineralogy book to find out what they were, because it's just incredibly diverse. You don't even have to realize what the different minerals are, but just look at the way the colors vary there. So samples to sample variation. So these are very, very varied rocks. So where does the Terra Rosa come from? Well, there are three possible places that the Terra Rosa comes from. It's residue left from the weathering of limestone bedrock. So the idea here is if you took the bedrock and dissolved it, you would be left with a residue that could not be dissolved. Okay? Number two, wind-blown material from the Sahara Desert. Number three, wind-blown material from North America, Mississippi Valley in particular. This debate on where Terra Rosa comes from has been ongoing in the geological literature for years. The problem you've got is, if I say to you, well, it's formed by the dissolution of limestone existed, well, we don't know what that limestone was. And if I take I've done it, I take the rocks from the Cayman Formation, Pedro Castle Formation, I dissolve them, there's nothing left. We run all the same geological analysis, we don't get any of the minerals that pop up on this. So unless there was a sequence of rocks on this island for which we have absolutely zero evidence of, You could say, well, they had another layer of rock that had all this and it's now gone. We don't have evidence of that. So that idea that it came from weathering of the limestone bedrock doesn't make a lot of sense. The idea that it came from wind-blown material from the Sahara Desert does make sense. And that's not a new idea. So, for example, Charles Darwin in 1845 and 1846, when his boats were anchored off some of the Cape Verde Islands in the Atlantic Ocean. This is when he was starting on some of his trips and study evolution. A fascinating individual. If you read some of these old papers, that he actually commented about, they were anchored there and there was a storm with strong winds, and while they were there, the ship rigging and the ship floors got coated with dust. And even then they were able to detect that it came from the Sahara. The advantage we have today, of course, is that NASA produces all these beautiful images like this one. You can see where Cuba is, and you see Cayman, and all the reds and yellows are showing the dust that's in the air. You see it here when you get those pink skies and that. And when we analyze the Terra Rosa from the mineralogy, from the chemical composition, I can definitely track it back to the Sahara. We can match. It's not perfect, but we can match and say it's come. We can't tell you which part of the Sahara, because different parts of the Sahara Desert have different geology, so you get different materials. We can't quite do that, but we can tell you that it makes sense for it to have come from the Sahara Desert. You had a major, one of these clouds come through the year before last. Hendrik here tried to collect some of the dust, but it didn't work. So we're still trying to figure out how we can do it. The way they used to, when they first did this on Barbados, they put big nets up in there, they put big posts in there with very fine mesh on it and stretch it across and catch the dust coming in. The problem we've got is that this dust is, the grains are so small. The grains in this are so small, we couldn't even get good images on a scanning electron microscope. The grains are less than 2 microns in most cases. So we couldn't even get images of it, and then I knew I was in trouble. But it's a fascinating story, but that's where it's from. Phosphate. Late 1800s on the island, phosphate was a major commodity. And this was a period in the world when phosphate was in great demand for farming and everything else. Charles Matley identified 5 places where the phosphate was mined. There were 2 on Grand Cayman, 1 just south of Georgetown, 1 up around West End. There's the west end of Little Cayman, and then 2 on Cayman Brac. 1 labeled P4. There is evidence that that was some mining there. P5 we don't think was ever. P1 and P2 on Grand Cayman, I've tried to find locales, I can't find them. I know where they are roughly, but with all the development that, there's no trace of it, or yet we can't find it. We have dealt with the one in P3, P4 and P5. As Cody will tell you, I've had him chasing around the island. We've been trying to find it. We've found some of it. But this is what the site looks like on the west end of Little Cayman. And what they used to do there, fascinating reading the old papers, that was at a time when Little Cayman had no population. So the people that mined there would live on Cayman Brac or Grand Cayman. Each Monday they would be taken over to Little Cayman by boat, work there till Friday and then go home. And the place where the phosphate was some distance inland. So they do this all, they had to mine it by hand and then if you look very carefully, right there and there's two pieces of iron railing. So they had a track that went back to the coastline, and they would have carts on the track, and they would have donkeys that pulled these carts out to the coastline, load it onto boats and that lasted for about 5 years. And the reason it stopped was that about that time there was vast deposits of phosphate were discovered in Florida. It was much easier to get it. It was cheaper to get it because you didn't have transportation. So the industry here on the islands collapsed. But that's where the phosphate was. And how do you get phosphate? Birds. Bird guano. So what happens on these is the birds, and of course on Little Cayman, I'm not saying these are the birds that produced it, but you get the idea. I mean, look at the tree branch on the right-hand side, covered in white bird poop. And when that reacts with some of the rainwater, you get a lot of phosphate-rich fluids going down in the ground, and that gets precipitated in these phosphates. Phosphates are, again, quite complex to deal with, but are also fascinating. So we think that on the west end of Lower Cayman, these are all from where there were bird colonies nesting.
Is it mostly seabirds?
Yeah, yeah. If you look at in the late 1800s, you look all through the Pacific Islands. The Pacific Islands, the coast of Peru, there was incredible amounts of phosphate were taken out. There was another island here in the Caribbean. My brain's gone dead. I'll think of it. But essentially, fundamentally, there were concentration camps. You know, you read the history, they put the gangs of people working there, paid them minimal wage, charged them for everything. They're under 2-year contracts. 2-year contract come, they weren't allowed to leave because they still owed the company money. And you can tell from this, I start doing this on geology and then I get engrossed and sidetracked into other stories. So some concluding remarks. We're near the end. Hey, time is pretty good. So here I'm going to put some very basic geological succession formed as a result of variable sea levels. Periods of high sea level, deposition. Low sea level, erosion. That's in the simplest forms. And it's the interplay between those two that gives us the complex succession that we see on the island. Knowledge of subsurface geology is critical to developing drinking water. And there, I'm done. You've heard enough from me. So, questions? And please, don't tell me there's no questions. Yes?
Under the dolostone on the stratigraphy,
Yeah.
fabric retentive.
Ah, okay. All right. Did I actually use that term? No. Anyway, so when you get a limestone, and then you get fluids that come through that start precipitating dolomite. So the dolomite replaces the calcite that's it. This can go one of two ways: fabric retentive or fabric destructive. Fabric retentive is where the dolomite crystals, generally very, very small ones, will essentially replace individual calcite or aragonite, and it's doing it on an almost one-to-one basis. So therefore the fabric is retained. Fabric destructive is where you can get the fluids come through which will produce huge dolomite crystals. And when you get those, that will destroy the fabrics. Right? I should point out to you, and I should have done this before, so I've answered your question? Okay. I've triggered my memory. mineral dolomite is one of the name dolomite is one of the oldest ones we have in geology. It dates back to the late 1700s when Diodat du Dolomy first described the mineral in the Dolomite Mountains of northern Italy. The following year, it was officially named as a mineral. Even today, we do not understand fully how dolomite forms. It's one of, and in fact, one of the things I've written a lot of papers on here is the formation of these dolomites. We don't understand it. Makes no sense. And dolomites found the world over. And one of the other projects I've been involved with over the last 4 or 5 years is if you go into South China Sea, I've not been there, but some of my ex-PhD students are working there, and they have islands like here, and you look at, I've got the photographs and I looked at all the data from it. If I gave you a piece of dolomite from there and one from here, you could not tell them apart. I couldn't tell them. If you gave them the blind, I couldn't tell you. They're the same. So there's obviously large-scale processes going on. We can't do it. And one of the big problems is we can't produce dolomite in the laboratory. We can produce it if you have temperatures of 200 degrees Celsius. But low temperatures that we operate at that 25, 30 degrees Celsius range, nobody has yet succeeded in producing dolomite in the laboratory.
Is it a timescale thing?
It might be. We don't know. There's something, there's got to be a trigger mechanism that we've not yet identified. And of course, because we don't know exactly how it forms, that leads into many other problems. Yeah. Geology is a never-ending stream of problems. That's why I'm in geology. I love it. More questions? Oh. Now, the teachers here, you'd be getting annoyed with your students if there was no questions.
I've got a question.
They're good. I knew that would get...
The lower valley well,
Yep.
it's got a cap above the obstruction zone. Is it
Yep.
getting replenished laterally?
Sorry?
Does it get replenished laterally?
Yes.
And
Yeah.
does it get replenished by like seawater?
Yeah. I've a strong suspicion, and I can't prove it yet, that despite the fact that we've got very high permeabilities, I can't believe, even though we're not that far from the coastline, I can't believe that we're getting sufficient replenishment from that. What I think is happening is I think there are joint systems and fracture systems that we know those exist in these rocks. And of course, if you've got a fracture or a joint that goes from that area out to the coastline, then those are really good pathways. We can bring in vast amounts of water. The problem I have with this, and it could be my calculations, but with the amount of water that's taken out there so consistently year after year after year, just relying on those permeabilities, I'm not convinced you could do it. So I think there are fractures coming through. And unfortunately, we have no way of measuring where fractures are. We can't, it can be done, but we haven't got the equipment to do it. So I think there's got to be, in addition to the permeability in the natural rock, there have got to be fractures in there that's allowing, yeah. Unfortunately, we can't measure that. Yes.
So, is there
Speak up so that
is there a
everybody.
chance that there's a freshwater lens in Little Cayman, or just wasn't studied?
As far as we know, no, there isn't one. Okay. There are, sometimes there is ponded water in some areas. We've tested some of that and it's saline. But we've got this headache on Little Cayman that we don't even have a well drilled there, so we don't know what's going on. The Water Authority have been trying to get wells drilled, another well drilled on Cayman Brac and a well drilled on Little Cayman, but trying to find somebody that can do the drilling to the specifications needed haven't been successful so far. I don't think there is freshwater lens. Usually on these islands, if there are freshwater lenses, the local inhabitants, especially the older ones and even past generations, if they were there, they would have found it because they needed it for drinking. Yeah. So as far as I know, no. Yes?
So just adding to the conversation about the freshwater lenses, they seem to be fairly well mapped, so it's kind of a two-parter. Do you notice differences in the characteristics of the rock on the borders of those lenses? And then the second part is this kind of fixed, or will the lenses change shape and depth, whatnot, over time?
I'm going to give you a bit of a long roots answer to this. You would think on an island like this that you've got 3 identified lenses. There were more, some of them have been, some of the smaller ones were destroyed. Yeah. Each of the 3 lenses are different. They've got slightly different chemical parameters, they've got different controls on them. So there's number one answer to you, is that each lens is different. So we can't just take the Lower Valley model and apply it to the East End one and apply it to the North Coast one. We do know that the East End, the characteristics of the water is quite, now I've got to be careful here. The fresh water, fine, you drink it. I mean, remember what levels I'm talking about. So fresh water from Lower Valley, fresh water East End, you can drink, no problem. From a geological or for a hydrogeology point of view, there are differences in the water chemistry. Sure. Subtle ones, but they're there. And that tells us that there are differences in the overall setting, because a lot of this is controlled by the interaction between the water and the bedrock. So the water doesn't just sit there, it interacts with the rock itself. You've got plant roots and everything else. So the water in the 3 lenses, there are differences between them. We can't apply a constant model to it. So have I answered you?
Partly, I'm just wondering then, like I said, how they're mapped, or is it subject to change in the shape?
Oh yeah,
size,
it can change, yeah. And one of the rules in geology, but remember that in geology we treat time on a different scale than nothing is static. Everything is dynamic. So those water lenses will change. If the climate changes to become drier, then the lens is going to shrink. If it shrinks, then you're going to allow more seawater to come in. If you get more seawater to come in, you're going to get intermixing with the fresh water. If you get over abstraction, so if the Water Authority allows people to take out too much fresh water, and that's what used to happen at Lower Valley, because it wasn't regulated. The Water Act here didn't come into place till 1983, and prior to that there was no regulation. You could do what you wanted. And the first thing they did when the Water Act first came in was to put regulations on Lower Valley, because that was the one that was being most affected. And these are very delicate things. Basically, once you've taken the fresh water is there because it's lighter than seawater. You take out too much fresh water, salt water comes in, but you can't then push it back down again because the fresh water is lighter. So it's a very delicate balancing act. You could change the structure of the rocks. You know, if you had an earthquake and big fractures, that would change it. You know, there's all sorts of things that can go sideways on things. Is that?
Yes.
Yeah, okay. Yes.
What happens with newer deposits such as like mangrove peat?
Yeah.
Does that usually erode away to harder rock?
Yeah,
over time,
I mean, theoretically, it could be preserved.
Yeah.
But what typically happens is that if you've got land sitting there with a peat moss on it, as you get transgression, i.e. sea level is going to creep up and up and up. And as that sea level comes up, it's going to erode away at anything that is not solid.
Yeah.
So sand beaches are going to disappear, peat will be disappeared. All the odds are is by the time you finish the transgression, the peat will go.
I've noticed some peat off of the Kimpton on some beach under the sand. There's
Yep.
mangrove peat right
Yep.
there. So that's the
Yep.
former line of
Yep.
mangrove.
I mean, that's what causes trouble up there. And I've been there trying to sort that issue out. Is that, you've got sand, peat, sand, and then every time you get a major northwest storm comes in, it does something different, totally unpredictable, and takes out the sand, leaves the point. Because the peat is, to some extent, is bound in place by the roots in it. That helps. But ultimately, it's not cemented. You don't get cements forming in that. That's going to go. Boy, I must have made myself clearer than usual this morning. It's only 3 questions. Either that or I've sent everybody to sleep.
Can you talk a little bit more about the process of reverse osmosis and the role that's like the rocks play with that?
Can I'm going to, this is me, I'm defeating myself here. What would be easier here, we do go to Lower Valley this afternoon,
Yeah, it's easier to.
and let me explain it there, and hopefully some of the Water Authority engineers, there's the man at the back. He's going to explain in detail exactly how it works. And I think if I defer answering that till then, you'll get much clearer. And if you don't, just throw something at me and remind me to answer your question.
Fair enough.
Okay? You moved your hand, so you can't do that. Final question. Are we ready for that? Final question.
When you were going through some of the slides, something kind of puzzled me. It was you were saying that there was a site that was good for trips, for food trips, and you were saying that the corals were perfectly
Yes.
preserved. But wouldn't that area come in contact with rainwater? Is it not considered fresh water?
Yeah.
Or it has to settle in order for it to.
Yeah. Your question is an excellent one, because in order for us to date the corals, for example, they've still got to be aragonite. Aragonite is unstable. So your question is great, because you think, well, if you've got a coral there, aragonite's unstable, the rain hits it, should dissolve and we'll lose it. It doesn't. We've got beautiful dates off those corals there, because the way we do it, we use uranium thorium, and we have to test them very carefully beforehand to see if it makes sense. And there are also, when we do that analysis, there are chemical markers that we can use to tell whether they've been affected. And you look at that and you go, this makes no sense. There is a coral that's been sitting out in the rain, and it's fine. And yet we can go and pull out some of the corals from the cores that we do. The corals are buried. They're changed. And so I cannot give you an answer to that. It's almost like somebody's put a magical shield. It's great for us because that means makes my life a bit easier. We can put a date on it. One of the things we constantly fight with in geology, it's our biggest headache, is putting an age on things. And it is so difficult. And of course, we need to do that so we can sort out the order of things. And yet you get examples like the one you just talked about that logically you would say, well, wasting your time. No, they were great.
Could a possible reason be that Cayman Islands, it's very hot
Yeah, but when you've got heat, that accelerates these processes. So, you know, it accelerates the chemical process. I understand what you're driving at. I think there is certainly an element to that. But you can go up there after heavy rainfalls, and certainly in the lower lying areas, there's little pools have collected. So I can't give you a good answer to that.
Would it be just that we're looking at the kind of freshest weathering phase that it's just working its way back?
It could be. It could be. I mean, to be fair, when we do these uranium, thorium, we do not use the outside part of the coral. So if we collected, say we collected a big coral head like that, we would take the sample from the middle, as far away from the margins as we can. In some cases, we like to do a number of samples to test it. So that can help. But again, we've done that, and sometimes it works and sometimes it doesn't. It's what we deal with. But if we don't, having that time frame is very important for us. Okay. Thank you for being so attentive.